No, I was really impressed with that.
Okay.
Good job. How are we
Okay.
doing?
I'm going to back off the game then. Okay. And we do that primarily by throwing a conference once a year, and we have some very specific goals in mind for it. We want it to be local to Portland. We want to prioritize speakers from the area. We want to keep it open to everybody, to people who are just entering into the information security world or the hacking world, or people who have been in it for a long, long time. We want to keep it open to everybody regardless of their income level. We want to make it as accessible as possible. We want to make it friendly and supportive. And so we do that by throwing this con every year. Now, we started, as I said, in 2011, and it's been going pretty consistently since then. The only exception was in 2020, we did it virtually, which worked super well if you were an attendee, but if you were an organizer, was very difficult. And in 2021, we actually just bailed on it. Honestly, we were all super burned out, and it was right in the depths of the pandemic. So we made the decision as a board to just not do one that year, mainly because we were like, nobody's got any energy to do this. Let's just pull back, rest up a little bit, and what do you know? And this is something for anybody else who's involved in organizations. If your whole staff is like super burned, taking a break and kind of having a fallow year miraculously gets everyone's energy back up again. Which is like, take the relentless grinder off. You can in fact do that. You have to be brave enough to say, sorry, we're not doing a conference this year, but you can do it. So 2022, we came back, and prior years we had it at the Oregon Convention Center, which was great. It was a relatively large space. There's some issues with the convention center from an operational point of view, but when we decided to come back, what we found was that because everyone is desperate to make all the money back that they lost during the pandemic, a lot of the commercial event spaces really jack their prices up, and we try to run pretty lean. Because we are entirely volunteer run and we are entirely sponsor and donation driven financially. So we ended up actually coming to PSU, and we were over at Smith Memorial Union last year. There's like on the third floor, there's like a big space auditorium, and we had one speaking track and one workshop track and a CTF for one day. That's a lot smaller than we used to be, and we had about half the attendance that we had last year, or prior to that. We were doing about 700 to 800 at the convention center, which actually makes us one of the larger B-sides. So we're about half that, but this year we're back, and I'm probably skipping ahead a little bit. So I'll take a little break and just say, who comes to these things? Well, last year I ran into somebody who was there with her mom, who had come up from Eugene, because, and the mom was like, I have no idea what any of this is, but my daughter's super into hacking, so here we are. And I thought that was fantastic. She was a high schooler. We have CEOs. We've actually had Ron Wyden come as a keynote. We have people who run local businesses, who work at companies from tiny little shops to giant ones like Intel. Huge variety of people. And as I said, we're going to be doing this year 2 talk tracks, possibly 2 workshop tracks, and a CTF. And I want to encourage you to come because, frankly, you don't need to, and submit whatever you might have in mind to our CFP, our call for papers, because you don't need to be an elite hacker. You don't need to be doing binary reverse engineering, although if you are, we'd love to hear about it. If you're doing something cool with hardware, if you're doing something cool with IoT security, if you just have a cool thing that you did with a drone or with a radio or whatever it is, we're probably going to be interested in it. And if it's relevant to security, broadly speaking, we'll absolutely consider it. We had a really fantastic talk last year about a guy who was using open source intelligence to track bike thefts in Portland. And tracking other people who were ripping off people's bikes. and incidentally shipping them to Mexico. So it was an international crime ring. So we're very, very broad-minded as far as our CFP goes. And hardware, since it's this audience, absolutely counts. I was at a con in December last year up in Seattle, and a guy gave a talk about voltage glitching. And if you have any experience in any of that kind of stuff, I'm sure the audience at B-Sides would just eat it up. So those are some random ideas. In the past, we've had talks about malicious USB cables, about how to break into information security. As everybody knows, the information security field is the hot field, or one of the hot fields right now. If that's where you're interested in thinking about going professionally, there's lots of people who are in the same boat, and there's lots of people who have been in it for a while who would love to talk with you about how to maybe break in. It's a great place to network and meet other people. We've done workshops on essentially airplane hacking. We've done workshops on data recovery from hard disk, which was hands-on. Take a busted hard disk and realign the heads in a miniature clean room. Lots of cool stuff. So, to sum up, we're small enough that you actually get a chance to meet people. Although we're kind of big on the whole B-Sides spectrum, I guess. We're sophisticated enough that you're going to hear some really, really good talks. We're friendly to newcomers and just generally friendly. It's Portland, after all. We're all pretty laid back. Everyone's pretty chill. It's very, very local, which means that the people that you meet there are probably people that you're going to run into in other places or have opportunities to interact with later. And it's easy to keep up those relationships. And finally, we have a pick your own ticket price policy, basically, that says, like last year, I think the lowest price ticket was $16. And then it was 32, and then it was 64, and then it was 128, and then it was 256, right? But that just, all that really does is guarantee you entry if we actually get to the point where we have too many people, and it guarantees you a badge if we have a special badge. But frankly, last year, a bunch of people showed up even on the first day, and were like, "Can I get in?" And we were like, "Yeah, for free." PSU students were showing up, whatever. We want to make it open to everybody. So, save the date. October 6th and 7th. CFP is open, or CFP. I misspelled that. CFP is opening soon. I don't know what a CPF is. Volunteer opportunities forthcoming. We got a great staff, fun to work with. If you're interested in volunteering, you obviously get in, no questions asked. We've got a Google group for email and Twitter. Our board meetings are open if you want to look behind the scenes as to how the organization runs. And I really, really hope that we will see you all and tell your friends. And if you want, I bet 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 stickers, so. Anybody want a sticker? Sweet. All right. Sure. Yeah. Hey, John. Sweet. Okay. And since we have 9 minutes, if anybody has any questions, I'm happy to answer them. Yep. Oh, I'm sorry, dude.
I have questions.
Yeah.
How does the volunteering work?
How does?
I like to participate.
Mm-hmm.
I probably could present. I don't want to present because that probably could be trouble.
Oh, I get you. Yeah. Yeah.
But I would like to participate in some other ways as well. So I think volunteering would be great. Can you give us some, can you understand how participating, how volunteering?
Oh, sure. So, like every convention, there's a bunch of setup before, although PSU does a great job generally with AV and that kind of thing. If you have any experience in the realm of video or that kind of thing, we actually stream our talks on YouTube. And we also obviously need people manning a registration desk. We need people just kind of circulating around, making sure everything's cool. We need safety staff. We're very keen on that. We need speaker wranglers. Find the speaker, make sure the speaker is in the room that they're supposed to be in at the time they're supposed to be there, and introduce them, that kind of thing. We even could at least use, if you want to do social posting, or if you want to do website stuff, or, we're very, very open on as far as that goes. And to your point about wanting to present or having something to present, but maybe not really, maybe you have some constraints on that. The talk about the bike theft thing, we didn't, you had to be in the room for that one, and no photos as well. Because the guy who was presenting it, since he was actually going after criminals, was a little bit worried about those criminals realizing that it was him that was getting them busted. So we will absolutely make accommodations if you want to do an off-the-record talk, or if you want to do it anonymously, or whatever. We will work with you on that. Anybody else? Oh, yeah.
Do you have things going on in between the conferences?
That's a good question. Generally speaking, we haven't, but I am trying to put together some kind of a pre-DEF CON meetup, sort of sponsored by B-Sides, for especially targeting people who are going down to Vegas for the first time, who might want to meet some people ahead of time so they can see some friendly faces. And I would definitely like to do more. That's another thing we could use volunteers for, is actually coming up with some things to do in between the conventions. Yeah.
I might have missed it before, but do you have more events throughout the year?
No, actually, we've typically just done the conference, but I'm hoping to get more activity, more things like that on an ongoing basis.
Do you have meetups or anything that's a little more casual?
We don't, but I can recommend the RainSec meetup, which happens on the last Thursday of each month at the Lucky Lab in Southeast. It's a really great community of people. It's like usually 30 to 50 people, a lot of whom are involved with B-Sides, and a lot of whom are, a lot of the usual suspects, I guess. If you go to infosecpdx.com, I want to say. Actually, maybe I should just do that. There is actually a list of local Portland security meetups that might be of use to you. Yeah, PDX-infosec, and I will try to get that on the display. There we go. Sure. And it's the second one. That would be a great place to start. 2600 is cool too. That just recently restarted, I believe. And there's OWASP, and Exploit Workshop is a really small one. So yeah, there's tons of stuff going on all the time. Oh, I should say also, if you are, if you're like, I have this really, really super cool idea or a great project or whatever you want to present, and you get your proposal accepted, we will absolutely work with you. If you have any hesitation about presenting, like you've never done it, we'll help you workshop your talk. We'll help you practice whatever you need to do. So it's a great place if you've never given a talk at a conference to get started. Four minutes left before you go run to lunch. Yes.
You said you are ever working on hardware hacking? What are you working on right now?
Yeah, I said I was messing around with computers since '84. Yeah. What am I working on right now? Well, right now, at my day job, I'm trying to apply. I'm trying to learn enough data science to apply it to the big, giant data sets of telemetry that I have access to in terms of scanning activity and attacker activity broadly across the internet. On a personal note, like I said, I just recently have gotten really excited about electronics and hardware hacking, and so I'm actually currently about halfway through a book from 1961 by a guy named Tepper, Tepper. It's called Basic Radio. It's in 6 volumes. You can get a PDF for it free on the internet, and it is the best book that I've found about sort of explaining basic electronics, and it has lots of cool like sort of 50s illustrations of like, look, there are waves coming off of antennas and that kind of thing. It's really neat. And so I'm essentially trying to get myself trained up on basic analog electronics and passive components, and then hoping in the next few months to start getting into more of the IC stuff. Maybe I should give a talk. Anyways. Well, if that's it, thanks very much for your time. And I hope to see you all in October. Please come.
When does the information part come out?
When we have enough information to send it out, it'll be sent out to the mailing list and also announced on Twitter generally. So keep an eye on those. The mailing list in particular, which I will put back up in case anybody wants to take a photo of it, is probably the easiest way to find out what's going on. Thanks. Have a great lunch.
start. When do you want? You're gonna just let me know when you're. Huh? All right. So we're
Okay,
ready. I'll
can I be heard?
introduce you and then
Okay. Is everyone still at lunch?
Yes. Very well. Good afternoon, everybody, and welcome back to the conference. We are here today with the delightful Pierce Nichols, who is here to talk about automated robotic sailing. And this is a very cool talk. I've learned a lot about it from Pierce over the years, so I'm happy to hand you over.
Okay. Can you hear me? Good. Okay. So my name is Pierce Nichols. Me and some other folks who I'll mention later, been working on robot sailboats for quite a few years now. We started a company to do it, so I'm going to talk a little bit about that. But this isn't really about the company, that's just context. What I'm here today to mostly talk about is how you actually teach a robot to sail. But we'll start with the context, which I love computers. Anyways, we're building, I thought I'd change that to, anyways, should be automated, not autonomous, cargo ships powered by the wind and sun. And basically combining the wind and sun with some batteries and regenerative electric propulsion gives us the sort of safety and schedule reliability we need to actually provide cargo services that people will buy.
So just some of the distinction you made between autonomous and automated is self-sailing
versus somebody's on board. There's a whole lot of stuff, and if you want to talk about it afterwards, I will gladly fill your ear with it. Anyways, so modern weather data and routing models make it possible to actually keep the schedules that customers expect. We're going to start with small vessels, 1 or 2 containers, 30-ish metric tons, serving more remote areas that get very bad service today. And then we'll start with optional crew because that solves a lot of regulatory and technical risk. So why we're building this thing. So first of all, fuel is half or more of the operating cost of your typical conventional cargo ship. It's massive expense. And all the ships in the world together emit something on the order of 1 billion tons of CO2 per year, and they tend to do it by burning very dirty fuel. Automation, sailing and solar power let us get rid of that expensive and dirty fuel without sacrificing the reliability or anything else. The other thing is, I'm sure you folks mostly probably remember the Ever Given from, I guess that's 2 years ago now. Anyways, the reason ships are getting that big is because if you're burning fuel and you're spending a lot of money to burn fuel, the easiest way to reduce the fuel burn per sort of cargo unit is by making the ship bigger, because you burn less fuel per ton mile or whatever. And that is the why we're building it. And as for who's supporting us, NSF was kind enough to give us a phase 1 SBIR grant. And we also got a little bit of pre-seed money from Deep Future Fund up in Seattle. As for the who, there's me. I got the team together, and one of the co-founders, Jeremy, Dylan, are my other 2 co-founders, and then Heather makes stuff like this certainly prettier than I could. And Graham has done a lot of simulation other work for us, which I'll talk about more later. As for how I got into it, so I grew up sailing on this boat. My parents ran a sail training and research organization when I was a little kid, and we basically bothered humpbacks from Dominican Republic up to Greenland. So how did me and my co-founders get to where we are? So a long time ago, in a Seattle makerspace, well after midnight, we were having a chat, and wouldn't it be cool to sail a robot boat around the world? Because no one had done it at that point. And we played with that for a while, and it's like, okay, we're doing this. This is kind of interesting. What's what can we do useful with this thing? That's not just some stunt, right? So data collection is interesting. And you know what? There are a lot of marine protected areas around the world. And patrolling and protecting those is kind of difficult. So you use a robot sailboat to do that. Now, when we started to sort of look at how to put a company together around this, we realized that there are a lot of autonomous marine data collection companies. The market's not that big in the first place. But at Maker Faire a few years back, when we brought some of our early prototypes, someone came up to us and said, can one of these things carry a few hundred pounds of stuff to Kiribati, which is way out in the middle of the Pacific Ocean, very long way from anywhere, therefore very expensive to get stuff there. And because there aren't very many people, big ships don't call there. So that gave us the idea of cargo. But that brings up the question of why, for thousands of years, just about all sea cargo moved under sail, but it mostly hasn't for the last century. This is actually the last big sailing cargo ship ever launched, 1926. And she, like most ships of her generation, is about as fast as a modern container ship when the wind is with her. However, back in late 19th century, early 20th century, accurate weather data was just not a thing. And the other thing is that handling all those sails takes quite a lot of labor, which meant that a ship like this, although it wasn't burning huge amounts of coal, did have quite a large crew on board. And after World War I, labor rates rose dramatically because the European workforce shrank by about 10 million people. And the only thing that kept them going through the 50s was that back in those days, if you wanted to be like a merchant marine officer, you needed time under sail. So all through the 20s, 30s, and 40s, a shrinking number of these guys were sailing, but it was all old men and boys. And there were some fairly bad accidents. But anyways, how does the sailing thing work anyways? So the oldest sails, like this replica Egyptian barge, are pure drag devices, right? It's like holding your hand out of the car window when you're driving down the freeway. Get a force on it, you go downwind. More advanced sailing vessels, like that schooner or the Hawaiian voyaging canoe, the sail forms an airfoil, right? And because you're generating lift as well as drag, you can balance that against the lateral plane area, right? So keels, rudders, things like that, to produce a net force that drives you upwind, right? Which means that you can sail in a lot more directions. Part of the reason I included the voyaging canoe here is because that kind of sail, which is called a crab claw, is actually one of the most aerodynamically efficient rigs that you can build out of just a simple soft sail. But it does take quite a lot of labor. So I mentioned sailing upwind. Let's talk about what that means and probably some terms to do with sailing. So if you're pointed dead upwind, right, case A there, you're not sailing anywhere. And if you're stuck there, it's called being in irons. And if you're trying to go from the wind coming on one side of the boat to the other, and you screw it up, that's where you end up. B is close hauled, which is you're sailing about as close to the wind as you can. C is what's called a beam reach, which is the wind's coming from the side of the boat. And that, for most sailing vessels, the fastest speed under sail is about that point of sail. Then as you turn farther downwind for a broad reach or a run, your sails are functioning more as drag devices than lift devices. And what that means for the speed of the boat, you can see what's called a polar on the left side, where you have the direction the wind is coming into the boat, on the angle, and then the speed that you can actually make is how far out the line is. As you can see, there's a whole no-go zone going upwind, and then downwind, because you're running away from the wind, your maximum speed also goes down. So let's talk about what the forces are. So the first thing that I need to mention for this is what's called apparent wind, which is the wind, if you're standing on the deck of the boat, that's the wind that you feel. That is not the true wind, because the true wind, you could think of as the wind that's if you're standing on a rock, that's the wind you feel. So the apparent wind is just that true wind velocity minus the boat velocity, and by vectors. The sail is giving you both lift and drag, which are at some angle to the wind. The forward force drives the boat forward, and then you have that lateral force, which you need to resist with lateral plane if you want to go forward rather than downwind. You also have the hydrodynamic forces. So that lateral plane produces a lateral force to keep you from blowing downwind, and it also, of course, produces drag. So the boat ends up propelled by the vector sum of the aerodynamic forces and the hydrodynamic forces. And if you're sailing at constant speed, it's all balances nicely. However, there's a little bit of a problem, which is that your aerodynamic forces are, at the center of effort of your rig, which is up over your head, and the hydrodynamic forces are at the center of effort of your, keel, rudder, etc., which is under your feet, right? Which means you get this big overturning moment that wants to roll the boat over. And boats resist that by some combination of where the center of gravity is and the shape of the hull. So sometimes you want to go somewhere that is upwind of you and that is within that cone of that no-go cone. So what you do for that is called tacking, which is you switch the direction that the wind is coming into the boat from side to side by turning through the wind. And if you do a number of these tacks to go upwind, it's called beating to windward. For us as a cargo vessel, who has to keep a schedule, how fast we can do this in terms of velocity made good to windward is a key part of, what sort of times we can actually schedule. Now, if you looked at the picture that I had earlier, you notice that the sails we have don't look much like conventional sails. That's because they're actually hard wings. Now, we chose those for a bunch of reasons, but probably the most important ones is they're more aerodynamically efficient. And the other is that they're way easier to control than a soft sail. That's because a soft sail has all sorts of weird and non-obvious boundary conditions between where it does something useful for you and when it just flops around uselessly, destroying itself. So that's actually somewhat hard to detect with a computer, especially since the way it's done if you're sailing a physical boat by hand is that you look at the sail, right? And that gives you a sort of difficult sensor problem if you want a computer to be able to do it. It's not impossible, but wing sails are better other ways. Wing sails also give us a place to mount a huge number of solar panels. Flexible solar panels are a thing, so we can just skin it. So that's enough of that. Let me talk about actual boats that we've built. Starting with our Pathfinder prototype, which it's only about 5 feet long. I could pick it up. Basically, we did this as the smallest, cheapest boat that brought sort of our key things together, and how fast can we get it working. The compute for it was, or the software stack was something called ArduPilot, which started life as a quadcopter control, open source quadcopter control software. But someone wrote some sailboat modules for it, which meant that we could just, plug it in and get going. And I had some Beaglebone blues from sort of earlier iterations. Beaglebone blue is nice because you have compute and an IMU and some other nice sensors on it. Final form of it is like what we have here, which we have trailing edge flaps. And then the wind vanes on top are wired into the feedback of off-the-shelf little RC servos. So you just, say, go to this angle, and it holds that angle to the wind, more or less. So first time we sailed that was about April of 2021. We sailed it a whole bunch in both Lake Washington and Green Lake. We're based in Seattle. And we really did, get a lot of sailing in with it. Some of these pictures are from Green Lake. Some of them are from Lake Washington. And, it's a small boat, so it is not a fast boat. And the hulls are basically just boxes with pointed ends. So, it's there as a proof of concept. It's not there to, to be a huge performer. We also found that there was a terrible problem with ArduPilot that we never actually managed to solve, which is that some combination of ArduPilot and our setup, when it was sailing to waypoints, would hit the first waypoint, go a ways to the second, and then just completely lose the plot and wander off. And we found a lot of things that weren't causing this. And we also discovered another bug in ArduPilot sailing code, which was the capsize protection didn't fire until about twice the roll angle it was supposed to, which was well past the point of no return. Anyways, so after that capsize, we decided that we didn't want to use ArduPilot long-term anyways for a variety of reasons, and we'd rather use PX4, which is from the same, also open source quadcopter control code. However, it has a remote console, it has modular software architecture, it has a whole bunch of things that are just better. So we rebuilt our control box around a PX4 and a Raspberry Pi 0W. We added cellular data, we added much bigger batteries, and a bunch of other stuff that made the boat a lot better. So that meant that I had to actually write some sailing algorithms and not just hack on something that somebody else had written. So conceptually, it's controlling a wing sail is pretty simple because you command the angle of attack, because the way we had it set up, you just command an angle of attack, which is, and if you're in sort of the lifting regime, so on a reach or close hauled, you want that under the angle of attack that the wings stall at. If you're going downwind, you'd like to set it so it's a great big wall that the air pushes on. The other fun thing is for a sailboat, you can actually, if you have more than one sail, you can use the sails to steer the boat. And you can do this with just about any sailboat that has at least two sails. For a soft sailboat, this is generally a pretty expert evolution if you want to do more than just trim the boat to maybe sail a little faster. For a wing sailboat, it's actually pretty simple because we can just set different angles of attack for the foresail and the mizzen, and they'll produce a turning torque on the boat. This turns out for us to be really key to make the boat actually able to tack, because if you leave the angle of attack where it is, when you try to tack the boat, it will just stop. And it won't do anything, because as you come up into the wind, suddenly you have a large aft pointing force vector. So you at least have to feather them. And our boats don't have a lot of inertia. So you need the sails to actually push it all the way around for the tack. The other thing is wind attack, right? Especially if you're sailing between waypoints. Now, the way we have done it for the boat, for what we've actually sailed, is by cross-track error, right? So you let the cross-track error, which is the distance from between the boat and the track between the waypoints you're going back and forth between. As soon as it reaches some limit, you tack back. And this is great for confined waters because you know the boat's going to be in this rectangle, right? And you can check whether that rectangle includes a rock very easily. It's, however, a little less efficient than it could be. What we've done a little bit of work on for more open waters is by looking at the best velocity made good towards the waypoint you're going towards, right? It's probably more efficient. However, you should probably only do it in open water because you're going to wander all over the map. It also means that you have to have really good data on vessel performance in order to get a good result, because you have to know, is tacking, minus whatever the cost of tacking is, going to actually get me a better velocity made good. If the data I have on that isn't good, well, I'm not going to make a good decision there. So March of last year, we actually got that SBIR that I mentioned. And the first thing I did with the first federal grant that I was ever personally responsible for as PI was I took a bunch of it out in cash, and I drove down to Oregon, south of here, and I handed a stack of Benjamins to a sketchy dude in a muddy field to buy a 50-year-old and therefore very inexpensive Hobie cat. Amazingly, the trailer lasted long enough to get it home. When we finally actually got some space, however, I was driving it down from my buddy's from Dylan's house, where it had been parked most of the time since I bought it. And the trailer tongue just snapped. Luckily we had a chase car who Heather was driving, and she just leaned on the horn. So we stopped, and luckily there were some very nice people who let us roll it into their driveway, and gave us a bunch of self-tapping screws and stuff. So we put a plate back on it, which got it the last 5 blocks to our new shop, where it promptly broke again. And we ended up building a new trailer because obviously the one it came with was way past salvage. So we took off the rig that it came with and all that, and we started putting together our wing sails, putting together the electronics. You can see early test getting it up in our little parking lot. Then we have the battery box, the battery charger. We have our power distribution box. Now, probably the most useful thing here is, you see there's there's sort of a black lump up in the upper right corner of that picture. That's the power relay. So all of the actuators and everything else, a robot this big, the actuators can actually do quite a bit of damage to themselves, to anyone who happens to be in the way, and so on. So we ran the power for all of them through that big thing, and then we ran the coil power for it through our e-stop switches. So if you smack the e-stop switch, it cuts the power to the actuators. So the actuators can no longer make it worse, whatever the problem that caused you to hit the e-stop is. We also have the brain box here, which has Raspberry Pi, a PixHawk running that PX4 firmware. The PixHawk also gets us the IMU and the GPS processing and a bunch of other useful stuff like that. We've got a little Daisy AIS receiver, which I think is sold on Tindy these days, and power distribution and fun stuff like that. So once we had it together, we could actually start taking it to the water. Our original idea, so I want to talk about how we mounted the sails. So the sail spindles are basically, the Hobie Cat has, on each hull, has sort of a stanchion coming up and a big corner casting that holds the whole frame, that holds it together. So we just drilled holes through the tops of 2 of the corner castings and dropped the masts in. Now, the way we originally did it was like, oh, we'll just, lever the whole, 20-foot tall sail with, a bunch of area up with guy lines, and then it'll just drop in, and this will be easy. It didn't work that way. It was actually quite terrifying when we tried to do it that way. So we added a hinge, which meant that we weren't doing that anymore. And the sails came up quite nicely, and then we were able to actually take them out and go sailing. We started with pretty mild winds because, we weren't quite sure how it would behave in heavier winds. The first time we took it out, though, it was raining, and it was 7th of January this year, so it was also bitterly cold. That's why we're all wearing the weird orange jumpsuits. Those are exposure suits. It turns a midwinter dip in Puget Sound from life-threatening to merely embarrassing. So I want to talk a little bit about what we actually did with the software and hardware stack. And this ends up pretty dense because there's a bunch of stuff going on. As I said, we have that main computer running ROS2, Pixhawk running PX4, and a bunch of other little bits and bobs. We have a 4G to Ethernet router because that lets us, instead of having to connect to the vessel directly, we can control it basically. It calls up to a AWS instance in the cloud, and Q ground control software running on a tablet calls the same instance and lets them talk to each other. Made life a lot easier. The sails also ended up each with a Raspberry Pi running ROS2 to actually do do all their controls. These 3 boxes are the inside of one of the wings. We ended up using knockoff Pelican cases because it's the cheapest waterproof case that latches and without tools. That's the other thing. When you're doing development, you will be in and out of your electronics all the time. Once we got it sailing a little bit, we added a couple of solar panels to the wings to test that. That middle picture, I think, is one of my favorite pictures of the original configuration because it's just taken from such a perfect angle by one of our friends. That was actually a little bit sketchy because you can see the back of that boat there. The guy who took this is standing on top of a wall, so I couldn't see that boat until we were almost on top of it. And just before this, I've taken a very sharp right turn to avoid hitting it. Because that would have been troublesome. We probably wouldn't have done it any damage, but it might have damaged us, and there would have been paperwork. So we actually did some simulation work as well. This is an overhead picture of where we did most of our testing, Shoal Bay Marina in Seattle. And that T-dock is where that picture was taken from. So we were able to refine this simulation to where we could pretty closely replicate actual trips that we did. So therefore, we think it is probably a pretty good representation, at least for low wind speeds. Now, one of the things about the configuration of the boat that I've showed you is that we had to put the sails up while it was still on land and then roll it down the ramp into the water, which if the wind is blowing 6, 7, 8 knots, isn't too bad. However, if the wind is a lot higher, it can be troublesome. As we found out when we started trying to expand our envelope. Because, well, you remember what I said about corner castings? So they're cast aluminum. They probably weren't great to begin with. By the time this happened, they were about 50 years old. And we drilled a big hole in the top of each one. So when we had it tied to the dock in about 16 knots of wind, we broke the corner castings. And then pretty much immediately rebuilt it with much heftier cross beams. That's like a 2-inch by 6-inch rectangular aluminum tube with I think it's 1/8-inch ball. So it's much stiffer. Basically, we took the same thing that we'd been doing, putting a spindle down into the top of each of the stanchions in the hulls and bolted them to our big cross beams. And then you can sort of see it, but it's a little hard to see. We have cross cables, or we have a pair of cable X's with the middle part driven apart, which makes this very, very torsionally stiff. We moved all the electronics boxes around from where they had been. And we've actually taken this sailing once, but we didn't have anyone take pictures of it on the shore. So I don't have any pictures of that, sadly. Anyways, so I put together a couple of slides of most of the software we used, some books that I've personally found hugely influential. All the really good diagrams in this were copied out of Aerohydrodynamics of Sailing. The middling ones I copied from Wikipedia, and the shitty ones are the ones I drew. C.A. Marquez, super interesting guy if you're interested in sailing at all. I put the Bolger and Smith books at the bottom because they sort of levered me out of the idea of what a sailing boat had to look like. And this is a bunch of software. Some of this I wrote, a couple of these modules are ones I wrote, the driver stuff. And then the rest is stuff that we were able to bring in for that. Anyone who wants to take a picture of this, get some of those links. Anyways, so here's some of the hardware we used. So some of the, I think, more unusual hardware. And the resources, Tom Spears, has a whole website about wing sails. Amateur Yacht Research Society is like the home for all the weird boats. And Eric Sponberg has done a lot of interesting stuff on unstayed rigs. So, any questions? Yes, Josh. Actually, let me bring you a microphone so people at home can hear you.
Okay, so I saw that there are solar panels involved. And you mentioned that you had a 100-watt panel, and so I'm curious, what was your power budget, and how much of the time were you above it and below it, and how much time did you actually capture the 100 watts worth?
So,
Do you need the microphone back?
No, I have one right here. So the solar panels are there to test that we were getting solar off the wings, right? They were not there to power the boat. Our actual operations, we were, doing day-long tests, right? And it's got more than enough battery power to do that. I think the farthest we ever drained it on a test day, 200 amp hours of 12-volt battery, was we took it down to about 60%.
What was your total power budget?
That depends on whether we had auxiliary propulsion on. With auxiliary propulsion, we were pulling about 45 amps off the battery. With just the wing sails, we were averaging more like 5.
Cool, thanks.
Yeah.
Yeah, so on the early prototype, you mentioned using servos as the mechanism that turn the sails.
Yeah.
What is it on the current iteration?
There's a big motor in the that's actually in that circular main spar, and that's driving the sail angle.
And it's continuous power to the motor?
Yes.
Okay. And I'm assuming that power goes up depending on the amount of angle
Yes.
required. Yeah. Okay.
Yes. It goes up in higher wind. It goes up if we're trying to hold a higher angle of attack. So it's actually a little higher if we're going downwind.
Thanks.
Are there other sensors in the sail monitoring like how much strain or torque is on the sail as you would?
Whoa, can you repeat the question into the?
Are there other sensors on the mast for things like strain or torque on the mast to give you a sense of how much push they're generating?
So the only one that sensors that we're using that are actually mounted on the sail are the wind angle of attack basically, and the angle of the sail to the boat. We haven't gotten to the point where we're doing the full strain gauge instrumentation. We're judging how much power we're generating by basically how fast the boat goes. And right next to you.
Just two quick ones. Could you elaborate a bit on how the trailing edge adjustment works on the sail?
So it's just like the flap on a wing.
Yeah.
Right. So if that trailing edge flap is fared to the rest of the wing, that's sort of the minimum amount of force you can generate. And then you deflect it, and there's a slot between the main element and the flap. So it's just like a slotted flap on an airplane wing. It increases the amount of lift you can generate, and also increases the drag.
And that's pivoting on the trailing edge of the solid wing.
Yeah, the pivot's actually a little forward of the trailing edge. That ends up being one of the way too many optimization knobs you have to twist.
And just out of curiosity, on the broader agenda, what do you expect the piracy issues are going to be with a boat out there all by itself?
So here's the funny thing about piracy. Piracy is basically a strong arm crime. It's like knocking over a liquor store on a larger scale, right? Some guys board the target vessel, point a gun at the captain, says, "Do what I want," right? Or "Do what I say." That doesn't really work with a computer, right? There's no one on board to threaten.
No, but I can just tell you what.
So boarding an uncooperative vessel at sea is incredibly difficult, right? If the vessel knows you're there and is maneuvering to avoid being boarded, it's basically impossible to do without a helicopter. So, and nice thing about the sensors that you need for automating a vessel like that is you have really good situational awareness. It's basically impossible to sneak up on. And there's always human supervision. Even when we go to full autonomy, there's always going to be human supervision on shore. And it's like, there's someone, someone's trying to get really close, or someone's very close. A remote human needs to deal with this situation. And again, if they actually manage to board the vessel, there's a lockdown computer system. It's got a lot of propulsive power, right? Like, it's perfectly capable of breaking a tow line. I think once we have full autonomy, it will be almost impossible to hijack one on the open ocean. And doing so is basically the same problem as hijacking it remotely, right? It's a computer security problem. And current pirates, it's not a bunch of hackers. It's a bunch of guys who knock over liquor stores on a giant scale. Does that answer the question? Yeah. Can you pass the Microphone forward.
Can you comment on the legalities and permitting required for doing something like this?
That is a huge thing. So the reason that we're starting off with crew on board is because that puts us squarely in the existing regulatory space, right? As far as the Coast Guard is concerned, we're a weird sailboat. There are rules for sailboats. One of the other reasons we're starting with such small vessels is we're under 100 gross tons. And there's a big regulatory step change for any ship at 100 gross tons. So under that, the regulations are pretty simple. Once you go beyond that, you have to get a classification society involved, which is not a bad thing. Or actually, not just if you go over 100 tons. If you want to carry hazardous cargo, you also have to become what is called an inspected vessel in Coast Guard, the way the US Coast Guard handles it, which means that you have to get a classification society like ABS involved at the design phase. None of the restrictions there are either unusual or even all that difficult to meet. They cost some money and they take some time. Full autonomy, the regulations are not there yet, right? And it is, at least in theory, possible to get the local Coast Guard office to sign off on it anyways. But that's an awful, but did the local commandant get up on the wrong side of the bed today? He is a hell of a risk to take. The Coast Guard is working on it. Coast Guard publishes a magazine like 3 times a year called Proceedings. And last summer they did a whole issue on ocean autonomy. And it's pretty clear that their head is in the right place, but the Coast Guard doesn't do anything. It doesn't make regulations quickly. So eventually there'll be regulations. I think they'll probably make sense, but they're not there yet. Any other questions? Okay, I think I'm just about exactly on time. I think my beard kept hitting the microphone whenever I looked down at my computer.
There's still a bunch of stuff.
Hello, can you hear me? Does this mic work? Do we have, this mic is not working. Do I need to do this little, hi, I'm Bob Hope. Welcome to Wheel of Fortune. No? Yeah. I have this thing here. Am I supposed to clip this thing? Do I clip this here? I clip this here. Ah, it goes not on my waist. That is a bad place to put a mic. I thought it was just a transmitter. Okay. Now can people hear me? Okay, great. Welcome, welcome. I guess since we're here at Teardown, and some of you hopefully have precursors, or maybe you don't, I thought I'd just have a session about precursor hacking. So the first thing I think would be helpful if maybe just went around and heard what people were interested in learning more about. Because one of the problems of precursor, and this is one of the problems when you have a product that has a dessert topping and a floor wax, is that no one knows what to do with it or where to start on it. So, and neither do I know how to start a workshop like this. So maybe we can start over there. And if you're just here listening in, just say pass. But if you have like a specific thing you want to get into more, go ahead and call it out. I mean, I have, just to give you the list of things I'm prepared to talk about, we can do everything from like customizing the case, talking about the electronics, the circuit board, my workflow. We can talk about Zeus. We can talk about the embedded controller. We can talk about the Wi-Fi stack. We can talk about the libstud. We can talk about Rust problems. We can talk about like, you know, all kinds of stuff. So anyways, go ahead and just say what you're interested or not interested in. Yeah, sure. Is the microphone working? And while you're doing that, I'll also pass this around. And everyone can feel free to just grab, I have some extra internal circuit boards for the precursor here, which you can just grab one of because I have lots of extras of them. And I'll tell you more about why you might want one of these in a minute, but just go ahead and grab one as you pass the mic around.
Okay, so I have no questions. Didn't know even precursor exists until 5 minutes ago.
Okay, sure, great, welcome.
All of those things you described sound very interesting. I'd be happy to learn in-depth stuff on any one of them.
Okay,
yeah.
Wonderful.
Yeah, the same.
Okay.
More of the above. Also, how the Rust stuff is kind of interesting as well.
For Rust is interesting too. Okay.
I work here. I also have a precursor. I unfortunately forgot it, but I'm most interested in kind of the FIDO2 and the secure.
Oh, FIDO2 stuff. Okay.
Well, and just key security.
Okay. Sure. Okay.
I've only seen precursor from a distance, really. So just because I'm here, it's an opportunity to learn a bit more about it. I would love it if you passed one round because I've never physically seen one.
Sure. Yeah.
That works.
Maybe you go first. I've never had a precursor, but I thought this looked cool.
Okay.
I make non-rectangular phones for non-rectangular people, starting with the circle phone. And I've had lots of problems with people adopting our phones as well, getting them over the ecosphere, even though we run Android. So
I couldn't quite hear what you're. I'm going to stand up close on the mic. Wasn't projecting. Can you say it again, please?
So we've run into the same problems too, having people adopt our phones because of, even though we say it's Android 10,
yeah,
it's still really hard.
Yeah. Okay. Yeah. Okay. Cool.
I'm just here to learn more about the precursor. I got to handle one in New York City a couple months ago.
Okay.
That's cool.
Cool.
But yeah, same. I've seen it for sale. I've seen some of the marketing for it, and just here to learn more about it, and hopefully put my hands on it briefly.
Okay. Great.
Cool. I've followed precursor for a fair amount of time. I'm most curious about just kind of RISC-V Rust interfaces, kind of how do you extend the Rust environment to new platforms?
Okay. All right. Rust to new platforms. Gotcha.
I'm interested in the entry-level learning and also the plausibly deniable database.
Oh, okay.
Find out more about that.
Cool. All right. Yeah, I'm happy. That's a kind of a soft spot for me. I'm happy to talk about that one.
Yeah, I mean, I'm here to get to know more about the device. It's the first time I'm hearing about it. So,
Okay.
Yeah.
All right. Neat.
I'd like to know how to get into the Precursor App Store, get through that approval process. No, I'd second the plausibility deniable bit database and the app workflow, the Rust app workflow especially.
Sure. Yep. Okay, and this dude's manning the camera. Got it. Let me just get a precursor to pass around. I am just making sure. I have one here we can use, but I just want to make sure, because I'm actually going to do something a little bit. Anyways, this is my actual password vault, but I'm relatively confident that you can't get my passwords right now in the mode that it's in, so I'll go ahead and pass it around. There is a little bit of, so the whole idea actually behind this is that it is using the plausibly denial database, and it's in a mode now where I could hand it to a customs officer and they can inspect it. So there will be, you will see some entries in here that are like my global entry number and a few other things, which basically you have to hand over anyways. But you can kind of get an idea of the mode that you can put it in for, like, you know, inspection by officials or whatnot. So that's running the Vault application right now. You should be able to poke at it and it won't fall over too hard, but anyways. So, all right, maybe it's worth spending about 15 minutes. I will give you like the rush overview of all the things inside of it. And then we'll drill a little more into sort of, it sounds like people are interested in Rust and the RISC-V stuff. And so we'll get into those. So we do have a screen here behind me. And how do I put something on? Oh, good. Look at this. So hello, this is the case. It happens to be, of course, open source. You can download everything. It's on our GitHub repo. I'm just showing you kind of just to get you an idea of the design process here. So this thing is a full model of the device. You can see that all the components are modeled through, so we can, it was very hard to get the clearance right here. And so of course we had to get everything modeled down to the component. Let me see. There you can see the cross-section view of the device here and what it looks like. Going through the device. So if you want to go ahead and hack the device a bit, the thing I want to point out is I did leave this part here. This back piece is a plastic piece. It's a radome. It's meant to actually, it's actually just big enough for you to stick a camera in there by intention. You could drill it out, put a little camera in there, and that little PCB I'm handing around right now is a replacement for the Flex PCB that's inside the device. And you'll see that there's actual pins labeled on there. So you can, there's actual solder pads you can actually solder down, and they go directly to the FPGA. And the pins of the FPGA is sufficient for you to like do a small CSI interface to a camera, or you could put an NFC device in there, or you could do I2C, your favorite sensor, whatever it is. And so if you want to go ahead and play around a bit with the hardware, you could do that. It was also designed with the idea that if you wanted to put an LTE module in, you would get a smaller battery. You would sacrifice some battery, but you could just shove the LTE module here near the radome, and then you would just do AT commands over UART to it or something like that to go ahead and get LTE. So it was kind of designed with a little bit of hackability in mind, despite being a very, very compact mobile form factor. 0 people have taken advantage of this, including myself, because it is a very small, fussy case, but I thought it was worth pointing out that there was a feature that I had designed into it. That's it for that, unless anyone's had any questions. This is the circuit board design. I use Boo Altium. It's not KiCad. Sorry, guys. I know this is an open source conference, but here I am with my proprietary tools. It's, you know, it's a PCB. It's a HDI, high density interconnect PCB. So I use this is the via in pad technique here to fan out. This is a 0.4 millimeter CSP. And so I'm able to do blind vias to fan out the CSP. And in doing a mobile device like this, you're required to do HDI because you can't get good parts for mobile devices that don't assume you have that technology. So that was kind of mandatory And we had a session yesterday where I'm trying to encourage more people to get into using this, this technology because it's pretty enabling for doing doing your own mobile device. Sorry?
Can we see test jig V1?
Sure. Test jig V1s. This is the actual test jig design for the device itself. It's a little faint because there's a little sun coming in, but you can, back here I actually have the outline of the PCB drawn in purple. These are the breakouts for the all the wires for every single voltage to the bed of nails that comes down here onto the device itself. This is a battery simulator. So this here will actually simulate the battery both in high load and low load mode. So I can simulate charging and discharge. Dummy loads for the speakers. Raspberry Pi plugs in up there. There's a USB interface up top. I have an audio jack that loops around into the device, so I actually test the audio. There's a full FFT, plays tones, cross tones, and stuff like this during the test routine to make sure the audio is okay. And then power supplies and voltage translators and stuff like that. So, yeah, I do. I should have a photo of that. Let me just see if I have one in my hot context thing here. Yes, you might be in luck. May not be a great photo of it, but hey, look, I'm on an SMT line. Let's see, does the photo, the photos are helpfully showing up over here, not over there. That's the SMT line that we use to build things. Let me grab this thing back over here so I can throw photos up. Let me see if I can find the test jig. Test jig, test jig, test jigs. A picture that kind of shows you most of it. This is the one without the test pins coming down on top. So there's actually like I have two versions of this. One of them has the voltage things that come down, and the voltage test is quick. They stick it in, make sure it's not going to catch fire, and they move it on. So I have one station that does the voltage test actually. It's like a, am I going to catch fire test? And then this one is the firmware burning station. The firmware burn takes a long time, so we have many more of these. I replicated this several times over. I actually do all my pulls for the firmware from GitHub directly. So the stuff that is, you can actually see what I'm running on the factory tester in our GitHub repo live. And I literally use git pulls to pull it. So when fucking GitHub messed up their keys, that was really annoying and still is annoying because I'm probably gonna have to fly to Korea to fix that because I did not ever consider that GitHub would mess up their keys as part of the scenario for my routine. Anyways, so and so this one here is, yeah, you can see the battery simulator, whatever it is, and like every time they update the device, I have like, there's two buttons. There's one for like go and one for function. So they, you know, this is one of my principles of test rig design, make it very simple. And when it runs, it just says, you know, the test. And when it fails, they'll say which chip failed, like check U11K, chip this one, like, you know, audio failed, whatever it is. So they'll print out the message. And then every time they do a firmware update, I have them send me the hashes that got pulled into the jig so I can confirm that it's all correct. And then there's some telemetry back to my server in Singapore so I can verify that nothing blew up along the way.
So you're using a flex there. You obviously don't have a bed of pins, right? You're using a flex.
The flex is, so the flex is actually, this is the normal debug port on the device itself that it exists on all devices, and that's where the firmware gets loaded. So this one's just the firmware loader. Sorry, this is going to be like a selfie shot. I think this is probably the only one I have of the whole assembly there. Let me see if we can zoom in the background here, the interesting bit here. That's the one with the bed of nails on it.
With the beer tap press.
Sorry?
With the beer tap press.
Beer tap press, yeah. So it's the welding clamp, actually, is what it is. Yeah, but it's a welding clamp. So they're originally developed for welding. So when you're welding a piece, you want to put the workpiece down, you fold it down, and it holds it in place. So they originated from welding clamps, but now there's a whole sub-market for these, so they call them test jig clamps, but originally welding clamps. Yeah, so this one has the bed of pins on the top. You can kind of see the wires going down the side, and I have a whole bunch of the other ones here that I use for firmware burning. So this is my last trip to Korea. I was just like, the big reason I go to the factory is to actually maintain these guys because they're really complicated and a lot of effort. And one of these actually exists in Singapore. If you go to ci.betrusted.io, let me go there on this website here. Sorry, 1 second. You can see the status of our CI system, and this is actually hardware in the loop. So when we do like the CTAP2 tests for compliance testing on U2F, we actually run the full CTAP2 on a live device on one of those jigs. It's fully scripted with TCL and expect. Every time we do a build of Zeus Core, it runs the factory test, which is the actual test that we run in the factory to make sure it passes the factory test. Then it does like an extended test where I do the PDDB. I do like a backup test to make sure I didn't break backups. There's a whole bunch of just automated tests that we do on the firmware side to make sure things don't break. And so this is like, it's all hardware in a loop. I use that exact jig. So basically, whenever we go from a release that we're ready to push, I've had very good luck so far in not breaking the factory, which is like super scary that you ship something over and a bunch of units start failing. That is like a nightmare scenario I really try to avoid. So that's our internal development process, if you will. So.
Sorry, does the factory rely on being online?
Absolutely. This is one of the benefits of being in South Korea. So it's not behind the Great Firewall. I have a gigabit line to the factory I can SSH in. It's not filtered. It's like great. Yeah.
So you have your own line to the factory?
It's the factory's line. Korea has great internet. And it's not filtered and it's awesome. And yeah, I can get hard lines to all the test jigs. And the other nice thing actually about working with the Koreans is that people in university learn Linux and command line tools as well. So most of the managers on the floor are comfortable typing command line. Whereas in the Chinese factories, typically they aren't, I find. So in the worst case, I can harass them to type a few command line things into a Raspberry Pi if I really get stuck. So it's like super helpful as well. Not trying to be like you should go to Korea kind of person, but that's one of the deltas I've observed.
Sorry, can I ask another question?
Yeah.
So that photo you showed, right, the selfie and we zoomed in on the background. Yeah. So there were 3 jigs. So and one's doing like power, and one was doing that debug interface, and one's doing the bed of nails. So every board goes through each one of those.
No, there's only one that does a bed of nails because it's very quick. So bed of nails is actually like that little OLED display. Actually, just live shows every single voltage on the device. So when it's not plugged in, it shows everything's failed because all the voltages are off, right? You put it down and it shows you the voltage, and there's like a little like white-black test. It's not red-green because it's a black and white display. And so the operator plugs it in, puts it down, and if any of the voltages are out, it's going to catch fire. Don't go past go. Look for shorts, and then so basically it's a pre-screen before you get into firmware burning. So you don't want to spend 10 minutes of the device roasting itself. It's just it's a lost board at that point in time, right? And then it goes to 3 identical jigs that don't have the thing on top. And the part of the reason I don't have the pins on top is you need to plug all the cables in, and the operator's hands will be stabbed by the pins. It's not very unpleasant for them to have that. So I actually take the pin housing off for the good of the operators. And you don't need to do that voltage test anymore. And it's a very long-running test. It takes about 5-6 minutes to burn the firmware. And then after that PCB screen test is done, it gets fully assembled, and there's a final, what I call an OQC test, where you go ahead and all the keys have to be pressed and has to associate with the access point, do some pings and stuff, just to make sure they didn't leave the antenna unplugged, that sort of thing. So,
how many have you made? How many have gone through that process?
About 1,000 now, I think, overall. Yeah, roughly, a little over 1,000, I think. So, it's enough that I found weird. I can really give you like war stories about weird problems we're finding now because we're doing full different lots of material. I want to point out that the 2 flex connectors that I have on the inside. So this is the one that is you observe there's a cable that goes to the test jig, and this is the debug connector. This is what you would plug into with the Raspberry Pi hat if you got that. And this is basically the way you unbrick your device. So if you go ahead and screw everything up, like you've just screwed up your FPGA, you self-destructed the device or whatever it is, and you want to recover it, this is the header that you use. It has JTAG for the FPGA, and it has access to the the embedded controller's SPI ROM, so you can program everything directly, even if everything doesn't work. And it also has a pair of UART headers, so I can talk to both the embedded controller and the main CPU through this. And this is the internal. This cable here is the one I just handed out. So you can see this one here faces into the battery compartment, and it's basically a hack connector. The main reason it's there is for the power pack voltages, right? That's really the only thing that's in there in the speaker. But you can see I have these GPIOs available. I have an I2C in there. I have the vibrator motor drive. And also I have a charger temperature sensor wire. But there, the pinout is chosen so they actually you can run differential pairs to it, and you can like potentially put a USB PHY in there if you wanted to on the FPGA, because an FPGA can do anything you want. And also one of the pins can be used to one of the analog A to D converters. So you have an analog input available there if you want to just put an analog sensor on the inside. So it's all there. You have the header. You can solder to it if you guys want to hardware hack. But I won't go into that too much because it seems like more of a focus today on the other systems. Okay, that is the quick tour, I think, of hardware bits. I'm going to move more into sort of the firmware stuff. Anyone have any questions? Yes.
Sorry, it's a boring question, but I was interested in the keyboard.
Yeah.
Like, where did you get some keyboard? Is it from somewhere? You found these, you sourced them?
Yeah, full custom. It's a full custom keyboard.
Oh, wow.
So the process is that, so actually if you buy one of these, you get 5 overlays inside. So the idea is that you can remove the bezel, 6 screws on the top, and the keyboard itself is held in with 3 screws. And the way you change your keyboard layout is you take the physical overlay out and you put a new one in. So I ship with a QWERTY, a Dvorak, a Xerte, Quartz, so it's French, German, Dvorak people like me, QWERTY normal people, and then a blank one, just a pure black. So in case you want to do Colmac or something like that, you could use a white Sharpie or something and write your keys on it. Or if you just want to be super elite and dark, you can just have a black thing. I know where the keys are, right? The guy is it's a really tiny event. I mean, these keyboards are very hard to source now. The guy has a really tiny shop, and the process is it's a sheet of polycarbonate onto which they build up resin, just a resin through a UV cure process. So this mold, they basically pour the resin in, they lay the sheet on top of it, it goes to a UV curing machine, and you can get about 1.5 millimeters height for the total key height. And then they cut it out with a CNC, silk screen color on the backside, and then they laminate onto it these little polycarbonate nubs that go to the dome buttons underneath. And then we have the dome button sheet itself on the keyboard, which is a sticker full of dome buttons. And it turns out that all that stuff is really fully amortized and depreciated, so you can get dome buttons and all these things really cheaply. You just have to find the right vendors for it. But they want enormous volumes. So I actually had to buy 3,000 of all of these before that's all the crowdfunding money went just to, I'm buying all the keyboards I'm ever going to need for the rest of my life from these guys with crowdfunding money. But the per unit cost is really low, which is why I just throw them all into the box. And when you buy the overlays on Mouse or Crowd Supply, all that price you get charged is all just shipping and handling. Like the product cost is de minimis. That margin is all just like pays for this conference and these guys' salaries and like some guy in Texas to put in a box and then postage. That's just the cost of shipping air basically. So, yep.
I was just curious, like when I try typing in different letters there, it was all sort of jumbled. Is there a reason why it's doing that?
You tried. Is it jumbled? Yeah.
To punch in some values. I don't know. Just
monkey size.
Yeah. So I was just curious, like, sometimes it was, if I press the key Q, it was printing exclamation.
Oh, if you press and hold, yeah. If you press and hold a key, it'll get you a different thing. But you might have the layout might have been swapped on it. I think is what might have happened. And also, it looks like someone did manage to crash it. Good job. I need to find the little pin to reset it because, does anyone have like a paper clip or something? I didn't bring one of those. Very good. I don't know how you guys managed to crash my device. That's what happens when you hand your device around, right? I have the nerve pinch. I got it, hopefully. Okay, yep, it's back. Huh. I wish I knew how you crashed it. Who crashed it? I want to know.
We can pass it around again.
Sure, you can pass. Oh yeah, someone changed the key layout on it, yep. So let me see. Let me swap the keyboard layout. Probably someone was just playing around with the keyboard layout and swapped it to something that's not the actual keyboard layout, which is why the keys came out jumbled.
I mean, it might be.
No, someone actually.
I might be the person who did that.
Someone actually changed the key layout.
But do you find you can type pretty fluently on that? Like you can find out text messages real fast?
I'm okay with it, yeah. I think it's not for everybody, to be honest. It's not like I gotten used to it, but I think a lot of people complain about the ergonomics of it. The small keys, yeah. I have heard from people that is one of the feedbacks that we're trying to.
Think about these, I'm sorry, there's a naive question.
Mhm.
Naive question, but could you use a BlackBerry keyboard? Could you use something that's already in market and get cheap?
Yeah, we thought about using like a BlackBerry keyboard, but the problem is then we're kind of limited, but to how many of these we can source, right? Because they're BlackBerry keyboards and they're not. Okay, the keyboard layout's fixed.
Can you pull out the
Oh, I don't have the Braille model with me. Yeah, we built a version of this that has Braille, so it's like there's no display at all. It's just like a solid screen, and it vibrates, and you can type Braille, and it has like the 6 keys on it. But I didn't bring that.
Braille, yeah, with the Braille display, with dots.
No, it doesn't have it. We actually put text to speech on it. So actually, all the menus speak to you with text to speech. And I don't know if you've heard like the text to speech that blind people use, but it's really fast talking. Like I can barely understand it. But the guy I was working with, like, yep, this is how I like it. So, yeah, and we routinely test the text to speech. That's part of the CI loop. So it's still working, even though we don't have a huge like blind user base. But there are a couple Braille units in existence, and a blind guy uses one, maybe. Hopefully he uses it. I don't know. I don't really follow up with him regularly, but yeah.
I'm sorry, it didn't make it all the way round, if you don't mind.
Oh, it didn't make it all the way around? Okay, sure.
What do you find most of the users in the precursor use it for? Since there are 101 possible uses.
The primary use case that I've seen, I mean, it's all driven by software, right? So the one piece of software that's most complete is the password vault. So the Vault application, which is the one that I left running on it, has U2F FIDO2, so you can use it as like your authenticator token. Has TOTP, so the 6-digit rolling over codes, and it has a regular text password vault built into it. Some people have added to it a Matrix client, so you can actually do some chat on it through Matrix. I think some other people, there's a couple other applications I've seen, like just people just developing stuff on the side. A guy's trying to port Signal to it right now. But I think primarily it's been for that one app, which is the most finished thing that we have. And the other thing people, I think, ostensibly use it for is like, I want to learn to code Rust. This is a great excuse to learn how to code Rust. So, yeah.
Thank you.
Yep. All right, so we will descend briefly into the layer of hell known as the FPGA design. I guess we'll start here. This is the source code for the RISC-V CPU. And why is this? Oh no. How do I get it out of this snap mode? There we go. Maybe you can see this? IDE? Okay, yeah. Great. So we use a VEX RISC-V CPU. You can see everything. We have a fork of it for our own use on the device here. And so let me see.
Where is the actual fork that we're using? I won't bore you with this too much if I can't find it. This is not the exact one, but it gives you an idea of it. So we can define things like how big the cache is, how many lines we have on the inside, where the IO ranges are, what branch predictor we use, how many multiplier plugins are in, all this sort of stuff. So that's all something we configure. One of the hints that I learned the hard way is that, so there's one guy who basically writes all this, and he uses an IDE called IntelliJ. And if you don't use his IDE, his code is really hard to follow. Like, I'm like, how does this guy even code in this language and whatever it is? And until this thing gives you the pop-ups and the click-throughs, you're just not going to follow the code. So really, I have an IDE just for hacking on his code base. So if you want to go ahead and customize the RISC-V CPU, you can do this. It's in a language called Scala. It's like a one left of Java bespoke language with this tool called SBT. Complicated. If you want to build it, I'll walk you through it. But you can build your own core, which is really cool. And then we use, I have a lot more pixels on my screen than this has. This is the LIDX file. So how many people here know what LIDX is? Anyone? Okay. So LIDX is a Python-based language for doing hardware design. And so this here is Python. You might recognize, yeah. Is this font just way too small? Should I just make this, try to make, you guys can see it? Okay. So yeah, I mean, it's Python. You can see all the imports and stuff. These are like the pin definitions for all the ports and stuff is an array. And then, yeah, like Python, all this Python. So if you want to go ahead and like say add another UART into it, you can go ahead and just throw another UART in. We have a UART mux, and you can have like an extra UART inside your device. Or if you want to go ahead and create an interface that goes to an LT interface in the inside or a camera interface, you would start here. This would be your on-road for hacking it. You run the script. It will call Vivado, which is a proprietary tool, to go ahead and do the compilation of the assembled Verilog output file. And I can show you what that looks like a little bit. So this Python compiles into Verilog. Oh, here. It happens to be right here. I was looking at it. So this is the actual Verilog description of the socket itself. So these two windows are like logically equivalent, but one is basically transformed into Verilog. And this gets plugged into the Vivado compiler and turns into an SSE. You can see all the bits and pieces. TRNG, blah, 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 all this stuff. So we have like dual TRNGs. We have like a local ring oscillator. We have a avalanche-based ring oscillator. We have a crypto accelerator. We have AES acceleration. We have a whole bunch of stuff on this thing. So anyways, that's the FPGA design. So you can go ahead and play around with that too. And then we can move more into the Rusty side of things. So, by the way, all this stuff is on GitHub. Let me just show you what the GitHub repo looks like. You can see, let's see.
Which functions does the EC do?
The functions of the EC are basically, the point of the EC is to be a power controller for the system mainly. So when the system is in this mode here where the screen is like showing this is a memory LCD, so this consumes almost no power. It's basically like e-ink. And then in this mode here, the EC is actually on and waiting for the wake up key press. It can also actually talk to the Wi-Fi chip, so you could potentially get like a packet from the internet to wake up the system as well. And that does the expensive boot cycle to get the SoC running and that sort of thing. And so that's its primary responsibility. It's a pretty small code base, actually. No, it's untrusted. It's an untrusted device entirely. It exists outside of the root of trust. And it has a completely different style of code base. The code base is also in here. I'll poke on that briefly in a second. But so this is the main repo. It is oddly named Be Trusted because that's what the project was originally called. And that's actually, from an overall project management standpoint, we want to build something that is not a developer tool, but something anyone can use for trust. But this is not that. This is a developer thing, so that's why it's called Precursor, and everything's domiciled in this repo for that historical reason. There's a wiki. I recommend you go here for all kinds of documentation. It tells you how to like get started, our matrix chat, how to update your device, how to set up security, passwords. If you want to go ahead and load apps, you know, the App Store, whatever it is, the instructions are here. Tells you how to do Hello World, all these kinds of things. And then we have like a ton of documentation on the OS. We have a Rust book. Where is it? The Zeus book. So this is a book which kind of goes through the whole system architecture of the kernel, gives you stuff about like how the system starts, talks about message passing, how to do the build system, blah, blah, blah. So there's a lot of documentation here. It's a little bit dense reading, but if you have any questions, typically that would be like one of the first places that we refer people to for these kinds of things. GitHub.com. All right. And so everything is in here. So Be Trusted Hardware has all of the hardware design files. So this is like, you can see the bezels here, the case designs, the internal FPCs, revisions of the motherboard, the hat, like everything. So if you want to do any of the hardware hacking, the Braille variants in here, all that stuff. What? Should be, yeah. Let me see. Case v2. Step files. They are step files, which you can then import into SolidWorks, which will have like, if you want the actual raw SolidWorks files, I can send it to you, but actually the SolidWorks files are kind of shitty anyways. Step, I think, is better for interchanged, to be honest. This is the embedded controller code base here. So you're talking about the EC. This one is a merged code base. So it's both the FPGA design and the firmware in one repo, because it's small enough that we can do that. That's rational. You couldn't put the kernel and FPGA in the same repo because it just got too unwieldy. Like, it just didn't make sense to push everything into one. But this one's really, really lightweight. It's just a tiny RISC-V, and the actual, it's so small I can even show you the code right now. Here, it's just these code modules. It's so tiny. It literally is just a main loop. It starts with like, initialize time, get your uptime start I2C, run the charger, and comes down into this loop. This is the main loop, and it just gets messages in, handles interrupts, does DHCP, looks for imutap handler, has a little parser, and then all the commands that it can handle from the host CPU in a big loop, and that's it. Like, it's just one big event loop. That's like the whole structure. It's all in Rust. Yeah, it's super simple, right? This is like about as simple as you get for an embedded Rust program, and it's intended to be very simple. Okay, so that's embedded controller. There's the book, the wiki, the sock is here. Like I said earlier, if you want to go and hack on stuff. Let me see. The Vexris core itself is here. This is the Scala file for it. So if you want to go ahead and build your own Vex, it's actually all just sitting here. And there's a little script you can run, build.sh, which it looks really simple. This is like all these tools, they look like one little command, but this will end up pulling down like gigabytes of libraries and take 20 minutes to run, and it'll fail 5 times through because there'll be dependencies that don't link and stuff like this. It's a whole thing. Looks simple, but anyways. Yep. And then the actual, there's a block diagram of the sock here. So yay, hey, documentation. You can see what's all the inside of it. So there's the core, USB debug, cryptography engines, TRNG, SHA-5 engine, Curve 25519 engine, audio, memory LCD, external RAM, and a whole bunch of other peripherals. So it's we have documentation, kind of. And then let's get into the Rust stuff for Zeus core. I guess maybe we start at the beginning. Life starts at the loader. And I can show you exactly where the beginning, very first line of code starts. So we use all inline. So basically, as much as possible, this is all Rust. There's no like C trampoline, there's no libc. So one of the lies of Rust, and this is actually very frustrating for some people who do embedded stuff, is that Rust is actually a shim on top of C. It's a very fat shim on a very narrow layer of C, but if you write Rust for any regular big iron computer, when you do like call to libstud.net TCP get or whatever it is, TCP, it actually calls libc underneath it. It's not native Rust. When you allocate a new vector, it calls cmalloc underneath. It's actually using the system cmallocator, right? Which is really, really frustrating for a lot of people who want a pure Rust system. In Zeus, we do it fully pure Rust. There's not a line of C in the system. You don't have to install a C compiler to build our system from scratch. So the very, very first line of code is using inline Rust. And this is it. Yeah, I think this is it. So this is the start, __ start. This gets located at the reset vector. We set up some trap handlers. We put a stack canary for the loader to make sure it says, let's just see if we overrun the stack at that point. Set the stack pointer, install a trap handler, and then jump to the loader. That's it. That's the whole preamble from the very first instruction, right? And then at this point here at Rust entry, we are now running Rust code, which is located here in main.rs. Oh, there it is, Rust entry. So then this is the loader, right? So the loader is really, really complicated. I'm not going to go into all the details of it, but one of the things you need to know about our system is it uses virtual memory. So we have an MMU. How many people know what virtual memory is? Okay. How many people know how to, have you guys ever done the whole like I start in real mode and then move to like virtual memory mode later on, or machine mode to virtual memory mode later? Okay. So there's this thing that happens where like your system boots and everything is physically mapped. And then at some point in time, your address instruction space goes to virtual memory. So all of a sudden, when you were at instruction 4000 or something, it's actually located somewhere in high memory. And there's this magical moment where all the offsets change, the whole world changes, and you have to set up for that. It's really mind-bending to set that up. So basically what this is a piece of code that takes every single server that we've linked in, figures out where they should be located in physical memory, creates a page table mapping for every single one of them in a page table that we're not using yet, runs all the way to the end, and then it does this thing where it says, okay, I'm going to cause a fault. And when you return from this fault, you are going to be in virtual memory, and this is my program counter. And so it then causes a fault. The fault handler says, okay, just return, it's fine. And then you're all of a sudden now in virtual memory mode, and we've closed the door behind us, so we can't go back to that, and then we're now in secure state. That's what this whole loader does. That's the dance that it does. It's mind-numbing code. It's very hard, but it's kind of cool when you understand how it all works. There are cryptographic signatures on all of this. So we have the secboot module, which we do an ed 25519 signature. There you go. We actually check the key signature here, and we actually have 3 different keys. You can see the code page. So if you self-sign, if we use a self-sign key, so, sorry to bore, tell me if this is boring to you, if you guys really want to know about the secure boot process. You guys want to know about secure boot? Okay, secure boot, right. So the idea is that you start and the FPGA has a tiny bit of ROM on the inside, which has its own secure loader. And that's supposed to be trusted. The very, very, very first instruction you run, obviously, has to be trusted. You can't have, that's just the way the world works, right? But the first thing it does is it goes ahead and reads out the next blob that's going to run, computes an ed 25519 signature on it, and makes sure it matches the stored signature, right? And if that checks out, it loads that block, and then we do that for the next thing, and so on and so on and so forth. So this one, basically, the model we have is we have 3 different signatures we allow. One is a self-signing signature, one is a third-party public signature, and the other one is the developer signature. So everything that we release, when you get a firmware update, it's signed with a developer signature. Anyone can actually sign with a developer signature, right? And if you look at a device, let me see if I have a demonstration of this here. Okay, so this one is actually a one that I'm doing development work on. If you look at the very, very top, there'll be like a little small line, a hash mark on the top. And that little hash mark, so you put like a very visible thing through the status bar to indicate that you're running a developer image. Because anyone can sign it, and then someone could take your device, put the developer image in, and then not tell you they did it. And that is enforced by hardware. It's actually like you can't undo that, you can't overlay it. It's going to be like this black and white hash up there. So you can't pre-compute an XOR and then try to put bits there and say, oh, I don't have the hash because I'm hiding it from you. It's like there, right? So a lot of people, when they first get their device out of the box, my device is broken. It has like this little hash mark on the top. It's actually a feature, not a bug.
So can you help me understand why using secure boot in a completely open source?
Because the idea, yeah, it's completely open source, but in this case, the secure boot is not to protect you from, keep you from running anyone else's code. It's to make sure that the code you're running is your code. So that like the scenario is like, I just passed my device around the room. You guys have all handled it and whatever it is. One of you could have actually just plugged it in and put some firmware on it without me knowing. If you did that, the only way it would boot and run is if you had this developer signature on that. Anyone could get the developer key and sign it. However, when I turn on the device, I would see that hash mark on the top and know that someone's tampered with my device. So the reason why we have the self-signed public key is that when you do the first, there's a little ritual you go through, you put this root password in and it creates keys and stuff. It actually creates a cryptographic key that only exists in that device itself. It's nowhere else in the world. It's actually inside of its root enclave. So no one of you would have that key. And then so when it boot back into this mode, I would know that that's the case, right? So that's the main reason we have the secure boot, is to detect, tampering and that sort of thing.
I was just wondering how you put that key in the device in the first place.
The secure boot. Yeah, so it's an interesting question. Another one of those like little guilty, like I really went too far down the rabbit hole doing this thing. So the actual key ROM itself is, you asked, so now you get the answer. I'm going to bore you with the answer. I have a helpful slide for this. GitHub.com, betrusted.io, SOC. Inside the system on chip, we have this. This is the key ROM. So it's a 256 by 32-bit key ROM, actually built into the hardware of the FPGA itself. It's not like burned into the external flash, it's in the bit stream itself. And this is encrypted with the FPGA's AES key. There's an internal fusible AES key inside the FPGA, so it's protected by that key. When you first initialize your device, we actually create, using TRNGs, a ED25519 key, which is just any random number, 256 bits. And we actually, through the F4PGA project, they reverse engineered the bit stream of the Spartan, the 7 series. So we actually go back into the bit stream and patch their key into the bit stream of the FPGA itself. So if you watch the little progress bar where it's updating, it says I'm patching the gateware. What it's doing is actually decrypting the gateware. So your gateware comes encrypted initially, but the key is all 0. It's the 0, it's not encrypted, but I mean, it's encrypted, but encrypted a shitty key, right? But we do that because we want all flows to be encrypted, even if they're not encrypted. And then it goes ahead and patches that to the key that you store in here. It's actually the multiple keys, but we'll just say the key and store it in there. And then re-encrypts the thing to that key, and then you're booting at that point with your key located inside this hardware key ROM device, right? And so that's actually located physically in the hardware. It's not like located in the file on the disk or anything like this. It's burned into the SoC. Yeah, that was like a very deep rabbit hole to figure that out, because I had to go into reverse engineering the bit stream and patching stuff and all kinds of crap like that. It was like fun, but maybe not a great use of my time. Yes, so that self-signed key is considered to be the trusted key, right? So that's when your top bar line is clear, right? We have an option for a third-party public key. So if you don't want to compile code yourself and you want to trust someone else, you can say, I'm going to load this third-party public key into the device, and I'll trust anything that comes from them. And I'll also have a clear boot bar if it comes from that person. So far, no one has stepped up and volunteered to be essentially a certificate root for this blah, blah, blah. Because it's hard. You have to trust that person. They have to have like some procedure for storing that key. We have to do signing with them, all sort of stuff. But it's built there. It's in the flow. And then finally, there's a developer boot key, right? So that's kind of like the three keys that are built into the bootloader. Other small kinds of interesting things in here is that when you first turn on the device, you reboot it, there's a tiny, tiny, tiny little graphics engine in it that can go ahead and render text to the screen. And it turns out one of the Rust's Achilles heels for small embedded systems is that when you do just a simple thing like, let me give you an example of something that shoots you in the foot. So here we actually, like, so for example here, print line, this macro here, print line, check fail, blah, blah, blah. This looks really, actually this one here, this one looks really innocuous. Sign length -4 is, this thing substituted into here, right? That turns into like 4 kilobytes of code or something like this internally. Like the Rust formatter is like really, 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 really heavy because they have to check all kinds of cases. They have to deal with UTF-8. They scrub things. They go byte by byte. They allocate memory. It's like they're terrible, terrible, terrible things. And so when you are building for a small embedded system, you have to really keep the amount of like format calls minimum. And so in the loader, we are very restricted in the number of format calls we use. We're actually careful to make sure we don't use, like for example, if we don't use hex digits anywhere, it'll optimize that out. But if we even have one call that has hex digits, and we only have the whole hex library pulled into format, and it's not even part of our main code base. And so when we first compiled this, half of our code was just format code because all the debug symbols that were in there, it didn't fit, and so we had to like trim that back. It's just one of those like little annoying things about Rust. Okay, so that's the bootloader done. Let's move on. We get into the kernel, and maybe it's better to show it inside GitHub because then you guys can know where the code is instead of looking inside my IDE. Let me see if I can navigate this by GitHub and not get lost. Where's my cursor? Here it is. Here it is. All right. So inside Zeus core, I'll go very briefly to the kernel, and then we'll talk about apps, because I think that's where people really want to get towards. So kernel, you boot into the kernel, and how many people here write Rust? Okay, actually, so it's helpful for me to even just tell you the structure of a Rust project, so you know what I'm doing. Okay, so every Rust project has a manifest file called a cargo.toml file. This guy here. This is where you start in a Rust when you do a Rust program. This is the kind of first thing to look. It has all the metadata, like what it is, the revision, versions and stuff, and it defines all the dependencies. I've never used npm, but here it's a little bit like one of those package manager type of things. And the cool thing about it is because we have this toml file here, it's not like C where you don't know what files are inside of your package or whatnot. So when you open up any well-formatted Rust project in IDE, everything is known, right? You can click through your methods, you can search through it. All the code relationships are there. It's defined inside this particular file. And then it's always the case that you either have like a source or a lib directory, which means it's source if it's a binary, lib if it's a library, and then you can look for your main.rs, which will, in this case, since it's the binary, you can be here and look for main, and that's basically it. So that's kind of how you can navigate your Rust code. So this is kmain, runs here. We have like some check with a panic if something doesn't work, and then this is the main loop of the kernel. That's it. This is the scheduler. That's the whole freaking scheduler right here. You're looking at it. Basically, it says, do I have a task that's runnable? If not, find the next task, repeat. Done, right? Super, super simple. And it turns out, actually, so Zeus is a microkernel. The only thing the kernel does is basically this and some memory management. So the kernel itself is like a few kilobytes, runs out of like 8 kilobytes or 4 kilobytes of RAM, and just coordinates all the applications. And the way the whole thing is structured is with message passing. So when you want to go ahead and say print something, you actually send a message to the print server. The print server gets the message, runs it, and says, I've done printing, and it goes and waits, and it idles, right? So actually, the reason why we don't need a scheduler is actually we delegate it to the system tick timer. The tick timer is actually effective with the scheduler. It's a whole nother process. The kernel can the tick timer can fall over. The system will be be quite unhappy because like you're not getting events and stuff. But you can actually, other processes can still run. So it's not like Linux where like if one portion of the kernel falls over, the whole thing stops. We can actually, like it's like the file system can fall over, and then we can still be doing debugging on the console. It cannot run in a system without an MMU. It absolutely must have an MMU. Yeah, and this is one of the sticking points of getting like on a Cortex-M, is they have an MPU. And this is an architectural decision we made early on. We want to build a secure system. And we're like, we have been using MMUs for 30, 40 years to build secure systems. We know how they work. We know all these things. And then there's these people who try to make these proprietary like MPU, like little add-ons and whatever it is. And they're not as well understood. The number of people can develop for it is like, I can count on 2 hands or something like this, right? And there's almost no code base and no papers on it. So we're just like, look, we have full access to the source code of the CPU. We're going to build a VEX with an MMU. So it's like, it doesn't make sense. And when we dug into the ARM ecosystem, we wanted to build like a Cortex-M with an MMU. They won't license it to you because ARM charges like a huge amount for A series. The thing that basically defines an A series is it can run Linux. And if you want to run Linux, they're going to charge you a lot more royalty for a core that can run Linux, and the MMU is the product differentiation point. So it's like it's a bright red line. They will never put an MMU in a low-end device because they want to charge you more for anything that can run Linux. Kind of annoying.
So in the RISC-V, now you have physical memory protection.
Yeah. So we have physical memory protection on a page-by-page basis.
Is there any plan to port Zeus into physical memory protection rather than MMU?
Physical memory protection versus MMU. What do you mean by that?
So physical memory protection is equivalent to MPU now.
Oh, the PMP. No. What? Physical memory? Say again?
Yeah, so physical memory protection block in RISC-V.
Yes.
Is the equivalent to an MPU.
That's right, the PMP. Right. Yeah. So that's what we're asking. No, yeah. We won't use the PMP either. Because again, the PMP, it's not proprietary, it's open source, but again, it's like, the number of people who know how to program for it is like, versus like I can talk, everything I told you about this whole virtual memory thing and the switch through, it happens in Linux, it happens in BSD, it happens in Mac OS, like there are bazillions of OSs that do it, and they're very mature and we know how they work. Whereas if I went to teach about the PMP, we would get in some arcana about like memory segments and defining these things and whatever it is, and I don't know, I just felt like that was not a good use of effort to try and it does restrict the number of CPUs that can run in. So right now we can only run on this FPGA-based device. But there is another group that's actually ported to an Atmel chip that has a A-series core on the inside. So we actually run an ARM now as well with an MMU. That actually is a thing that is possible. So you can run on a Cortex-A ARM now with Zeus. Let me tell you about the message passing inside Zeus, because we're going to become very necessary to understand this to get to the next few bits of facts about how the Zeus system is organized. Cursor, where are you? There you are. Great. Messages and message passing. It's almost like I intended to be here. So the way the kernel works is that you have a server ID, which is a random 128-bit number. It's different on every single boot. It comes from the TRNG. So the kernel actually has its own TRNG port. It gets cryptographically secure numbers. And the security of the system comes from the fact that it's very unlikely for you to guess this number. So unless you choose to disclose your SID, no one can talk to your process, right? That's the default state. We have a name resolver, so you can choose to register yourself and say, hi, I'm the codec service. You can send me messages, right? And then you can look it up by the name, the codec name, connect to it, and it'll give you its server ID. But actually, you can have multiple server IDs inside of your process space. You can have your private space, your public space. You can firewall it. So we do a whole bunch of stuff to try and make that. And the other thing we do when you connect by the name server is that we can actually tell the name server, I will let you connect exactly 2 people to me, right? So we do what's called TOFU, trust on first use. This is like SSH. Do I trust this key? Yes. You store it, and then if it rotates, it like gets mad at you. So we can say we want to be discoverable, but only by the boot set of processes. We expect 2 people to talk to us. Once those are claimed, no one else can claim us again. So it's another feature we have to sort of restrict access to your programs. Anyways, we have server IDs, and what happens is basically every single process sits in the sleeping state. You can have 30 processes. They basically, that little schedule I told you, they all sit in that sleeping state. And then when a message comes in, say you hit a key or the timer goes off more typically, it'll go ahead and wake up the system. You'll process the message. You can send other new messages, trigger those sorts of things. They go into a dispatch table, get put in the message queue, and then it goes in the schedule to see what's runnable at that point in time. That's the whole like kind of loop system on inside of it. So one thing you'll notice about this is basically async, right? If you do any sort of async programming in JavaScript, the whole system, the whole task system is async. So we actually, it's kind of weird because we don't have an async layer. We don't have a talk IO driver or whatever it is. But we looked at what it would take to do the async layer. It's basically just exposing this API to do it. And actually, we have to undo a lot of this to create the fiction of the standard library calls because they're not async. So we actually have to create a bunch of synchronous mechanisms to hide our async nature of the kernel. But that's the core mechanism on the inside. And I said I promised not to use my ID, so let's go back to GitHub. Probably by now you want to run some apps. And the place where those are located is up here. So inside Zeus Core, just at a high level, the services are located here. These are all the kernel services. So this is like the Curve 25519 engine, the SHA-512 engine, the graphics server, input method editor, low-level I/O, the PDDB net. Those are things that you probably don't ever really need to touch or play around with, but if you want to look at them, that's where you find the services. That's in the services directory, right? The locales directory have we'll get into that later. But basically, you can actually support Japanese, Chinese, French, and text-to-speech out of the box right now. So you can, if you want to contribute like a translation, you can add a translation. Everything's like made for internationalization and translation. The apps are located here, the apps directory, and we have a few of them that are kind of available, baked into the system. We have a Hello World app. We have the Matrix command line chat app. There's a REPL demo, so you can chat back and forth, like response eval, reply loop kind of thing. There's an app called Transient Disk. So what this is like, it's actually just like it reveals a 1.44 megabyte disk when you plug it into a computer by USB, and it's all in RAM. So if you want to sneaker net some keys from one computer to another and you want to make sure it's wiped, you fire up Transient Disk, you plug it in, you copy your keys to it, put it in another computer, reboot the device, and it's zeroized. So you don't have to throw away USB drives anymore, right? You can use this for that. There's the ball demo, which is just a ball that bounces around on the screen. And then there is the vault. This is the big Kahuna app right now. And so this one here has the entire, I think Scott was asking about the U2F stuff. We have actually, what we've done is we've pulled in, this is actually OpenSK, which is the Google reference implementation for FIDO2. And so we pull that in and we make a target for that. So we're pretty compliant in terms of, I think, our FIDO2 implementation by the nature of our code base. Let's take a look at What's inside hello? Let's look at hello world. What did I put in here? I forget.
Does any given app take over the whole USB port, or do you have multiple concurrent?
Yeah, multiple concurrent. Yeah. So it can, but you can only have one endpoint active at a time. So you can say I'm now currently transient disk, and you can switch to the Vault, and then now you're a FIDO2 interface. But yeah, it's not. We can, for example, have both keyboard and serial console available if we were to reveal both descriptors at the same time. So it's like really how you set the descriptors. Yeah, okay, so this one just prints hello on the screen. It's literally like a little hello world dialog box. So you get the loop, and so this is that loop structure I was talking about. You receive a message from the kernel, you do a dispatch based on the message ID. If you get a redraw, it'll just redraw and just puts hello world on the screen. If you quit, you quit. That's it, and you terminate the process. That's like the simplest possible program. It does nothing useful at all, right? Just prints hello. We have another app, which is the ball demo. So this one shows how to do like rendering of a ball that bounces around on the screen. And so this one here is a little more complicated. We get a redraw. We have a thread that pumps. And what it is actually the pump thread. Do I have it here? It's not here. The pump thread is probably in this module. Sorry, let me just see if I can find where I put it. Yeah. Okay, so we actually start a thread, and you can see here is a standard Rust thread where we do stand thread spawn. So it's just a standard Rust thread call. And in order to do the animation, we have to continuously say what's the rate of animation. So this here just sets a timer to run at some interval and says move the ball position, and just keeps on doing that to itself over and over again. If we don't have this pump thread, nothing runs, right? You have to have that as one of the threads that gets spawned. And then that sends a message to the main thread, which calls redraw, which then causes the ball to bounce around the screen, that sort of thing. So that gives you a general idea of how it works. So one of the cool things about doing development is that we have multiple emulation modes. So you don't have a precursor maybe, but you can still write Zeus code, because we didn't do, say, cargo xtask run ball. So cargo is Rust's package manager. So you cargo build, cargo run, that's how you kind of invoke Rust, right? Xtask is like makefiles, but Rust versions of makefile. So Xtask is our makefile script. And then we have a verb, which is run, which is to run in the local emulated mode. And then we can specify the apps. So we can say, I want ball and I want REPL. So what this will now do is it's going to go ahead and on my slow laptop, build the entire system from source. And it will actually run it in what's called hosted mode. And so in this case here, I'm running the kernel, all the surfaces, everything locally on my laptop with an emulated screen. And actually I'll show you what it looks like in a minute when it finishes running. And so you can actually develop most of your UI stuff in this mode without ever having to load anything onto a precursor device itself. If you actually start getting into hardware, we actually support Renode, which is a near cycle accurate hardware emulator. And Zobs, who's the collaborator who did a lot of the work for this, made the Renode emulator really, really, really accurate. You can do a ton of you can do networking, you can debug the standard libraries on it, all sort of stuff. So if you want to do that, so you have a lot of options to develop code without even having to touch hardware. And then you have finally build for hardware target, and you upload by USB or by the JTAG interface to do things. So this is a slow little laptop. It takes a couple minutes to build the whole kernel. You can kind of see all the modules that's building along the way. Maybe while it's building, I'll say, do we have any questions at the moment?
The possibly enable
Database, yep, okay.
where does that fit into all of this?
So the PDDB is a service, and it slots into the standard library where the file system would go. So normally you have studfs like open, studfs close, and what that does is that it will create like key value pairs inside of a database which has plausible deniability. And the reason why I call it plausibly deniable is that it has a property where if the database is in its secured state, no one can prove or deny that they have secret data inside of it. The thing starts initially just full of random data. And then as you allocate data, we have a mapping system to map out pages randomly inside with your encrypted data. All the ciphers that we use have this property where the encrypted data is indistinguishable from random data. And so then as long as you don't reveal your basis password or your key to that data, if someone says, give me your device, I'm going to dump it, I'm going to analyze it, you can say, no, really, I've given you all my passwords, right? Like, you have all of them. They can't say, no, I think you have more passwords based upon the amount of free space you have available or how the thing's behaving. That's like not a thing that they can do. So that's the idea behind the plausibly deniable database. It finished building, but it put the window helpfully over here. So this is what you get. You get this emulated window. This looks like the UI you guys are just playing with. And we can interact with it right here on the screen. So we can go ahead and switch to app. And we can go to the ball demo and see this is what the ball demo does. This is like the thread pumping along and moving the ball on the screen, and it's bouncing when it hits different things on the wall. We can switch to the REPL demo, and all the REPL demo is just, it tells you what commands are available. There's only one command available, and you just type stuff into it. And it's like, you can basically, the idea is you can just like add commands in here. So if you want to build your own little shell interpreter, it's like a thing you can hang off of it. And every single app, you can see here, there's like these little tabs that are showing in the bottom of your history that you type. That's just inherent in the system. So that's not part of your app. That's the input method editor service. So you can basically get a history of the last 4 commands you type. You can just punch the F1 to F4 buttons to recall those commands. So yeah, that's kind of like how you would build an app and play with it. So you can do that without, you don't have to have a precursor. You can actually start playing with the Rust code today. If you want to go ahead and add your own app, you basically would start with one of the templates that we have. I would probably just say fork it. And the easiest thing to do is just take one of the templates and start editing inside of it, because there's a little bit of complication in adding your app to the system. But if you actually want to make a full app, you have to add it to the manifest. And there's a JSON file here where you say, this is the name of my app. This is the name of the context. And then you have to give it the name of your app in all of the supported languages, right? Ideally. Some people just leave them blank for languages they can't translate, but it's nice if you just throw in a Google Translate and put something there, so like it doesn't break our CI system if you try to merge it in. And then this will always look for, this one here, we don't have the translations for this one. It'll break if you go ahead and try to have that in Japanese. But then, yeah, you would just add your directory here, put your app inside of it, and then it actually automatically pick it up when you say cargo x text run my favorite app, and then it'll go ahead and find your app in the manifest and build it into the system, and it'll be in the image. So that's running in hosted mode. If you want to build for actual hardware, you just do cargo x task app image, and then my app, you build it. I'm not going to run that because it takes a minute to build it, and it'll flush the cache. And then what it'll do is it'll create a Zeus.img file, which you can then upload by USB into your device. And then you can, it takes about 2 minutes if you have an Intel CPU. It takes 30 minutes if you're running AMD or Mac because of some quirk of the USB drivers. So USB is a little painful to upload the images on, but we haven't been able to figure out that bug yet. So that's kind of building apps for it. If people want to go ahead and start playing around with it, they can do that. Is there anything else people want to sort of dig into in particular on this? I mean, there's a lot of different topics to go into, so it's like.
Just on apps, what is the most crazy app that you have seen that say, wow?
Probably the Vault app is the is the killer app, right? And that's the one that I kind of, you might have saw in the unit I was passing around. It has a TOTP, it has the passwords. The passwords actually support like BIP39 natively. So if you're storing, I can show you the UI for it, but basically it has like a live, there's the BIP39 is a list of 2,000 words that you can fix. So actually as you type them in, it will correct the words for you and autocomplete them. And then also it will like compute the checksum. So if you typed in your word wrong, it won't let you accept it, these kinds of things. So it has like a bunch of like hooks and features in it for password management. And it does U2F stuff, so.
Do you see this debug infrastructure becoming network available or like removing a way that makes it more practical to have like your thing just plugged into it to do some target?
The debug infrastructure, what do you mean?
Right now, all of the cargo X-task stuff requires the physical attachment to the device, right?
No, so our cargo X-task run is all running on this device. My precursor is not plugged into here. That screen is actually fully emulated using OS native calls.
Right. But if you wanted to debug a Zeus process on a physical device, you would have to have the physical debug.
That's right. Yeah.
So do you think that infrastructure will eventually become more like, Android development or something, where you just have your precursor in your laptop?
So what we do typically, if you need to debug something on a physical device, we use Renode. We go into the emulated mode, and that one you can just stop and dump the whole. It's like way more powerful than debugging on a device, because debugging on a device you have to go through GDB and step, and it's like annoying. Renode can be like stop, dump everything, like your God mode. It's like much more powerful to debug in Renode. So if we can, we'll debug in Renode.
Yeah. How about the kind of inverse where you're just like running a remotely downloaded chunk of code from the device itself?
You mean, can we like basically have a runnable app that we get from remote? Yeah, we don't support that yet. We have to build it into the image because there's a whole loader and signing stuff that we have to deal with. So we don't have like loadable apps per se. Yeah. We don't have that yet. That's something that's like on the wish list of things that we're probably going to introduce at some point in time, because people want to be able to do. It'll be faster if we don't have to like copy the whole kernel over. If you're just doing an app update, it'll be way faster over USB. But we have to do a lot of rework on the loader and the OS dispatch system for that to work. Yeah.
So when you run Renode,
I'll turn on the lights here.
when you run the Renode emulator simulator, how close does it correlate to the real device?
It's really pretty solid. Yeah. Like yeah. There are very few. It simulates bugs and crashes really reliably. Yeah, it's really impressive how well Zob's tuned in Renode to emulate device. It's like bug accurate, which is really hard to do. It's a lot of effort to get that level. Oh really? Okay. All right. Okay, I thought maybe. Well, I think it's like, unless people want to like, if you have a device you want to actually start hacking on it, I'm very happy to like sit down with you and start hacking it, but I also recognize there's a lot of interesting things going on here. So if you don't actually have a device and I've kind of talked through everything, feel free to like pop out. But if you want to actually get into something in particular, I have all my hardware here to go ahead and develop. We can log in, do all sorts of stuff, whatever it is.
So I assume you've been working on the Vault app lately, right?
That's been, my focus.
Do you want to just like show us your features?
Sure. Yeah, I can show you what Vault looks like. So probably easiest to show it on the screen here in hosted mode, because we can do that as opposed to trying to do anything else. Let me see. Cursor. Cargo, Xtask, run Vault. Okay. And then I'll turn off the light so we can see the screen again. Maybe it's more interesting if I had some test records in there, but.
How would you cross the boundary in the Rust code for the ETL to to the accelerator that you have on the FPGA. So you have a very large structure complex that has
I can show that to you. Right. We'll do it on the browser because then you can find it later on instead of in my weird environment. So that would be inside apps, nope, core, services, engine 25519. This is the driver for it. There is, we have actually a pretty good online data sheet which shows you like the architecture of the engine, all the math on the inside, how to write code for it, theory of operation, blah, blah, blah. This is all there. You can find, knock yourself out, right? The actual driver itself. So when we have drivers, you see this is the structure here. We have both a main and a lib. What happens is there's a main program that runs, and there's a bunch of library APIs that go into it. Probably better to start with the lib side of things. So then we have like, you create an engine 25519 object. That's what you do. You create a new one of those. And then on the object, we have methods like start a Montgomery job. So this will do a Montgomery multiply, and it has some data structure for it. And it passes like all the parameters through the system to the main function. So then that thing is packaged into a message. And so one of the interesting parts is that that's a memory message, and we use the virtual memory system to make that very fast. You basically have your messages in your own process space. We don't actually copy the data. We actually swap the page table mapping. So what happens is you had that page of memory in process A. You want to pass that page of memory to the engine 25519 thing. We actually just remap the page table into there. And so then there's a page table remap without copy. Now there's a hole in the memory space here. It means this process actually can't mutate that piece of memory. It actually prevents, it's actually a very rusty way of doing it. Then this guy can go ahead and operate that structure, mutate the data, pass it back, and then we have the copy back in the native process space. So it's like this.
Yeah, that makes sense. And that means that kind of this main file now issues whatever the wishbone messages.
That's right. Yeah, this has all of the there's like these assembly opcodes for the different like curve 25519 operations. It loads them into the engine. So you self.copyreg job.blah blah blah, and then calls self.mp start. Yeah, so this is an example of a very low level call. We don't use, so most Rust people use what's called the PAC library, Peripheral Access Crate. It's from the TOC project. I personally hate it because I'm a C/hardware guy, and I find Rust syntax really laborious, right? If you use the PAC crate and you want to write data to a register, you have to use a closure. If you know what closures are, so it's like you have to do like double bar this, pass this thing in with an argument. It looks really awful and heavy. It compiles down to just one store. Trust me, right, is kind of what it looks like. I don't like that. It's too much magic. So I have like this, I built my own little crate. And so you have self.csr. WFO means like write field over, like writing the whole register over, not just field, but like it's writing the fuck out of the register, right? So it reminds me that's going to happen. And then we have like the actual hardware mapping here. That's the actual register window and the argument. That's it. That's a low level call for the system. Yeah, that's what it looks like. Yep. Yeah. Okay. Yeah.
Consider implementing that as a RISC-V instruction set extension instead of like something.
It's a little bit too complicated for that. AES is actually a RISC-V instruction set extension. That's actually like a custom RISC-V opcode. And it's AES, you almost have to make a RISC-V instruction set extension because the cost to context switch to pass 128 bits of AES and then decrypt it and then pass it back is more than the decryption operation, right? Just the passing of that little bit of data, running the engine is like a lot of overhead. So with a RISC-V instruction set extension, it's in your native process space, you run it, and then you actually get an acceleration. But just message passing overhead is like huge for AES. I mean, you can do like pair blocks and whatever. There's a whole bunch of like things you can do if you're doing bulk data, but it just turned out that instructions are way better. Whereas this here is like curve 259 was so heavy, Montgomery our Montgomery whatever multiplier, whatever it is, huge block of data that we can afford all the marshalling, and we still get a substantial speed up. Yeah.
So in order to kind of try to support, virtually you have to do with Zeus in general. Some extensions on the RISC-V processor. Like, is there actually support in the compiler, or do you just inline assembly it?
Oh, when we do the extensions? Yeah, I'll show that to you in just 1 second. One thing I want to show you, if you want to know where all of the registers are in the system, they are located inside this thing called UTRA-lib. UTRA stands for unambiguous thin register abstraction. So that's the thing I just showed you with like the WFO, whatever it is on it. And then this here actually contains the, after some preamble code, this is the full list of like, this is where the keyboard base is located in memory. And then these are the fields for resetting the sock and that sort of thing. So if you ever want to sort of get a cheap like hardware reference manual, it's kind of your C header file version of it. For the RISC-V, you're talking about the AES extensions. That is handled inside.
You have like some LiteX magic that adds that as an additional target alongside JSON and like SVD and stuff. Or...
Yeah. This all comes out from LiteX. So LiteX puts on SVD and we turn it directly, and it's all automated. So every time we build the sock, we can get a new SVD file. Yeah. It's all automated in the build system. So if you went ahead and you added like another peripheral to your Be Trusted sock and you put the SVD file in the right place, it'll pick it up and then you'll have those calls automatically. Yeah. So, right. So where is it? This is not the right file. Bunch of. Yeah. So basically, this is what it looks like. We just have these inline assembly calls, which is like, this is the actual instruction and then ret behind it. So that's how we call those individual CPU instructions. So when we write the actual assembly core, yeah, then you see we see vex AS dec ID 0. This is actually translates to that instruction with those arguments, and then we abstract back up into the standard AES library from Rust Crypto. Does that answer your question? Okay. Okay, you wanted to see what Vault looks like. I have to find my cursor again. Here it is. All right. So switch to app, key vault. Okay, so it starts out in FIDO land. There's no keys found because we haven't connected this into a host or anything like that to give us FIDO. So this is what the TOTP looks like. So you can see it has like the little 30-second countdown timer on the top to say how long you have left on your 6-digit number. It gives you a 6-digit number, and every single time you add one of them, you get another entry inside of that vault. And then this is what the password thing looks like. So I don't know, I had some, you can see I was just making bogus entries for testing things. So close menu, F4. So we can go ahead and edit one of these items. And so this one here, like the way we do BIP39 is that if you just put BIP39 as the first words here, it actually will show you the password rendered as BIP39 as well. So it stores the hex string and then gives you the BIP39 code as it may be. If I want to go ahead and create a new entry, so add new item, name it Teardown. Bunny blah, blah, blah. So there's a password generator here you can use. It suggests you one, or you can type BIP39 to generate a BIP39 password. If you hit backspace, I can say how I want the password to be 16. I can say if I want uppercase letters and numbers only. So instead of symbols, in case you have like some weird site that has these restrictions, and it'll give you a new random one. This is all using the internal TRNG, blah, blah, blah. And we've created like that entry. I can now add another item. Teardown BIP39. This one might be a little painful to work through because I don't have a BIP39 code, but if I do, now I can go ahead and say like, go ahead and autocomplete, whatever, a bunch of BIP39 characters until it's acceptable. And then I can go ahead and say, actually, no, I don't want to do that anymore. There we go. And it just aborted out of that flow because I don't have a BIP39 thing to put into it, but it'll validate the whole thing for you. This thing also has, when you use this in U2F mode, FIDO mode, most tokens, when you plug them in, they will just show you a little flashing light, and you don't know what program called it up. This one will actually print the relying party's ID. So if you're trying to log into like, fastmail.com or whatever it is, let's say fastmail.com is asking for your like authentication, do you accept, as opposed to just a flashing light. So that's like a little extension we added. And that's why there's even like this, the UI for FIDO here. Normally you wouldn't list the number of sites that you have, but if you were, every single time you have a residential key or something like that, it'll add it to there. Another feature of this is that it actually works with SSH so that you can actually put the key inside this device. So if you're an SSHing, your signing key can go inside your precursor. It'll make a little fake private key file, which is actually just a pointer to the device. And then it will actually pass the data to the device, sign it, and move it on. So if you want to go from host to host without having to move your private key and you just keep it in the device, you can plug it into another device, disclose the key, the public key and the pointer to it, and then you can use your device on a new host without ever having to have your key touch that host. So that's another feature that's built into the U2F stuff. So yeah, that's kind of the quick penny demo of.
Do you have a way to like actually simulate a USB connection in the?
No, I cannot simulate USB connection in this mode. And I think we cannot do that either in Renode. That's one of the things we can't do. So USB is a little painful to debug because it has to be on real hardware because it's very real time. I think there's a question back there.
Yes, I actually brought my precursor, which is still not unwrapped. And I didn't know if it would be worth it. I thought everybody was going to bring theirs. And so.
I thought so too, but a lot of people forgot. Yeah.
And this may be one of the hurdles with my phone is just encouraging people to unwrap it.
Yep.
Yeah. Would it be better to do that right now with this one, with everybody watching?
Sure.
Show how we get up and running.
Sure. Yeah, we can go ahead and we can do it. Yeah, we can.
My laptop.
No, I can use my laptop.
My laptop's Windows, but we also have Linux as well.
Yeah, actually, we have an overhead camera here, so we can just people can see what's going on through the overhead camera. Yeah, totally. Totes. And we can see how good the quality control was of my process. You can turn on that light, maybe. Is there a light that we can turn on? From the top-down view there. There you go.
Thank you.
Perfect. Hey, unboxing live on the internet. Okay.
And I'm sure you have videos of unboxing.
I don't have
I
anything.
couldn't find
You can use the update on the original one without this. Yeah, it's now reliable enough that we can do that, and I should be able to just show you how that works. We'll try. We'll see. You know, unscripted demo. Here, I actually got a Poke tool here. I can help you undo this. Yeah. So you're one of the original backers. This guy's been in its box for a while. I'm curious to see how the battery fared. That's like one of the big, yes, one of the, yeah. Did it puff up? Is the screen broken? All the questions. Yeah. Okay. Yep. So this is the device comes in here. It's I deliberately use this paper internal. A lot of people note that like it breaks during shipping, but the option is I use foam, which is not recyclable. It's a lot more stiff. But I was like, you know what? You're going to get this once. I don't want to ruin the world, so you get paper. terrible. Yep. So pip3 install precursor updater hyphen upgrade. And it's always good to kind of run it with the upgrade anyways, because sometimes we have bugs that like break previous versions of the things. And then I can say Python 3 -m precursor updater. And what this should do is it should automatically pick up the device and just run the update. In theory, it should be that easy. Let's put it on the .cam and see how badly I do. Okay, so I'm going to run that command. Oh shoot, I lost it. I can't see both at the same time. There we go. So okay, I'll show you what's happening here. Is it's actually gone online. It's identified what the kernel and the loader and the gateware pre-staged all the items into it. And if we go to the .cam, the screen doesn't look interesting, but it's frozen right now because what's happened is actually it's now in USB update mode. It's in this like special failsafe mode. And then we can watch the paint drying of data copying to your device. Closer. So on a like this kind of device, the Intel laptop, you can see it's probably kind of acceptable times to write updates, a couple minutes, whatever it is. If you're running a MacBook M1, it takes half an hour or something like this. I don't know why yet. We haven't figured it out. But there's some. We use libUSB in Python to do it, and so there's something in the interaction of libUSB and MacBook Pros, and also Ryzen chipsets that cause it to run really slowly. But Intel chipset, it works decently well. So yes, so this is basically the whole downloading process.
Does this help some? When, like, I've gone to this GitHub repository before, but I'm not about like stars. I mainly got distracted by like how many people were committing.
Yeah, is it a dead project or not? Yeah. No, it's a fair thing to look at. Yeah. Yeah, we should probably do like a click here stupid version of it, right? I think the part of the problem is that it is really like too many things to too many people all at once, and the information is too diffuse and hard to find. And I think now that we're actually getting enough users, I get a feeling for what people actually want to see versus what they don't want to see. There are some very loud people who want things a particular way, and if I cater to them, then like this repo structure gets weird. But then most people they just want to do it in a particular way, but I don't see them using it that way, and so I don't make it that way. It's like really, so it's restoring the loader. It's the last step. Let's switch it back to the .cam, and let's hope that it all works. Oh, let me go. Okay. Yeah, so this has a little QR code you can go that shows you how to reset the device if it doesn't reset. There you go. It reset itself, and it will complain initially that the SOC version is too old because it hasn't picked that up yet. There you go. And now there's a secondary process that goes through where it's updating the embedded controller. So now it is actually, I've staged all the artifacts in memory, but the embedded controller itself has to be updated by the main CPU. So now it's doing that update process, and that takes a minute. So it's now writing the gateware and the firmware from the embedded controller, and it's going to update the Wi-Fi firmware. So it's another process that you go through. It's a bit of a dance to get you from our very first release to where we are today. Everything has been changed. Everything is updated. Everything's terrible. But there you can go. So a couple other things in the UI. There's these little like lines on the back here. These here, every time with something backgrounds, I call it defacement. They're random lines that are drawn to prevent someone from taking. If someone sees your background and tried to give you a fake password box, you would see those lines drawn on top of something that is not supposed to be there. So there's actually a trust level associated with every single UI element, and we tried to make sure that you can't get like a fake, like password UI. It's like someone sends you a BMP that looks like your password box and you type in the password. So it's like, it tries, the whole system is like paranoid code around this kind of thing. So. Yeah, so again, paint drying. There's a lot of paint drying involved. And so I'll give you a preview of kind of what happens next. This thing should reboot. And it's going to ask you to do this ritual called setting up your keys, right? And this is the point at which you have to pick your root password, and you'll pick a boot unlock password later, right? So you pick a root password, and that takes about 3 minutes, 4 minutes to go ahead and re-provision those keys, re-encrypt that. And what it is you're doing is re-encrypting FPGA ROM to that. And then the typical thing that happens next is you reformat the PDDB. And that takes 15 minutes because you have to write 120 megabytes of cryptographic random data. It takes a long time to generate that much data and format that amount of cryptographic data. And then when that's done, your system is now ready to use. So it's a bit of a journey to get to that point. But we prefer to be, it's all done in the user's hands because the units shipped to you generic. Everything, all the cryptographic stuff is generated by you on your device after you've inspected it. We don't do it in the factory for you. The whole idea is it's done by you in the privacy of your own home on hardware that you trust. Okay, yeah, so this is now, yep, so this is doing the gateware update. So that black, when you see that black screen, that's actually reserved for the highest security processes. So there's only, when you see that black screen, this means like something from one of the most trusted processes doing it. So this one's actually writing the firmware, the actual SoC is being rewritten right now by that process. And now it says, please unplug the cable so I can reboot, press any key. So I'm gonna follow its instructions, unplug the cable and press any key. And so it says rebooting now. If the system shows no valid keys, error, or something else on boot, that you can go and do a hard reset, but it looks like this is working fine. Yep, okay. So there you go, you've now successfully updated your firmware. You're now running the latest stable release. A couple things I'll point out is, I said earlier, there's this, will it show up here? The screen resolution. Yeah. Yeah, it doesn't show up. There's a little stipple mark across the very top bar here because you haven't initialized your keys. It's saying that you are booting on developer keys. So if someone swaps out your firmware image after you sign it, whatever it is, that'll show up. That's not your screen is broken. That's a security feature. This thing's asking, do you want to set up the passwords for Precursor? You can say, I'm ready, not yet, maybe later, or stop by. You know what I'm doing. So I'll just do not yet, maybe later. I'll let you set your passwords yourself. And then you go into this mode where we can type on it and we can say like, help, and they'll show you what commands are available inside of the thing. And we can like check sensors and run factory tests and these kinds of things on it at this point in time. But there's no PDDB, you can't run the vault because there's no place to store data. The whole bunch of things don't work. So it's basically in a kind of a diagnostic mode that I leave. Like I think on future releases, you may not even get this console initially because it's confusing to users. So like, the device isn't working, it's not working. I'm like, well, you have to set up your passwords first, right? But for developers, it's helpful to have this. But anyways, yeah, that's it. That's you're now, yeah, updated. Let me see what your battery's at now. The 6%, so we'll let it charge a little bit longer. Let's see, what are this? There's a preferences menu in here. You can do Wi-Fi settings for connecting to Wi-Fi. There's a Wi-Fi kill switch, set up the auto backlight, you can set the keyboard layout, time zone, blah, 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 all that sort of stuff. That's in here. The main reason we have Wi-Fi on this device is because TOTP requires you to have time. And anyone who's built a watch knows that watches without a source of time will eventually desync by like a few seconds to 10 seconds a month. And that's enough to throw off TTP. And so the killer feature for Wi-Fi is NTP. We get time through Wi-Fi. That's why you want to connect Wi-Fi on a secure device. You know, we could probably also write USB drivers that set time or something like this, but since we have the Wi-Fi stack, that's kind of how you get time. So usually what I do is I'll like turn it on maybe once every couple of weeks Wi-Fi, let it do NTP, and then hit the Wi-Fi kill switch and just leave it disconnected. Now we don't have to worry about that. People suggested put GPS in there. People said like, well, there's like that radio signal that is transmitted. That you can buy a chip that like. There's a lot of ways you can get time, but time is one of those things that's really hard to get. So we have Wi-Fi, we use it. And so that precursor update is just for updating. If you're doing development, there's another thing called update underscore US Zeus or something like this. Update USB. It's in the tools directory. I can show you where it is. Updating your device. Zeus Core tools and all of the little helper scripts are here. So for example, USB update.py, you would just run this directly. So now we don't have the Python package. You just do, I assume you know what you're doing. This has not been made idiot proof here. And yeah, there's a 39 password array, blah, 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 blah. Let me show you that this is all the commands. So you can say USB update -k, and you point it to your Zeus.img files with your apps on it, and then your apps will show up on your device, and it'll only update that piece. But you can see there's a very extremely comprehensive list of things you can do with this. It kind of is an all-in-one tool for doing things. I have a small diatribe at the moment. The bit39 list is inside this library because freaking Bitcoin people made a bit39 library, which is fine, except that it includes the whole freaking world of dependencies. And you have to be running the latest version of Python. And so when I use their version of the library, no one could run this script anymore. It was really annoying. So now I just manually implement my own bit39 word list, so I don't have a dependency upon the rest of the world to have this one. It's really, this is Python, right? A couple other things, if you want to do internationalization, there's this internationalization helper script, which will go ahead and list all the translation files, alphabetize them, and so you can go ahead and add a language a little easier with the internationalization script. There is a backup script here, so if you want to do a backup of your device, which is recommended if you're putting high security stuff on it. Two things to understand about device, and this is very confusing to a lot of people. This device, as it is right now, ships with what's called the 0 key on the FPGA. So when you want to run a backup, you'll be like, why is my backup key so low entropy? It's just 0000000, because you haven't set that key yet. There's another thing you can do where you say, I want to burn the backup key on it, and it is a one-way door. It is no backseas, you can't return this device because it is a very high security key. You get one shot at it, and but you can do it, right? And I suggest you do it if you're going to put high security data on it. But you should do that step before you run backups because otherwise anyone can decrypt your backup, right? Once you have that, then you can actually run the backups, and the backups are like I just store them on a regular file server. I feel really comfortable about it. It's all my passwords and whatnot because the key is in this device and it's nowhere else in the world. And then if you are debugging the PDDB, there are bugs. We have the Backalizer, which can analyze your backup and pull things out. So sometimes some people have had some really terrible consequences where maybe they screwed something up terribly or they were developing and they lost some passwords or whatever. The Backalizer can usually pull out intermediate records. The actual implementation PDB, it's journaled. So actually the old records can be found if you know where to look for them, that kind of thing. And then there's a restore script here. So if you lose your device and you have a backup, you can run restore. And the restore will actually, you have to have your original backup, that key that you burned into it. You're given a bit39 word list. Write it down, put it someplace safe, do whatever you do with your highest security keys. That's the one key you have to remember. You type that in, decrypts the backup, sticks in your device, puts it with the 0 key initially, but it's all decrypted and you have your data back, right? So you can restore to your device as well. Hopefully that should all work. Yeah. Yeah, I mean, I think we can, it's cheaper to just order another device, but yeah, I mean, if you end up really screwing something up, then I can find this. Okay. I think that's all the time we have, right? Okay. Thank you. Go ahead and.
Yeah, there you go. Oh, no, no. Like that or something, but okay. Otherwise, you're good there. Okay. And I think we're on a short spot. Okay.
Yeah, yeah. Okay, so you all saw, you saw, doesn't need much of an introduction, but for your watching, he's going to be.
So I only have a handful of slides for you guys. I really think this is a more interactive section, so once we have the kits, you guys can go ahead and build it in. But you know, this is designing and building and watch grades for watching. So a lot of the things that are here are specific to game, but they also cover just doing graphics on displays in general. We start off by an e-ink primer. So how does the ink work? You have tiny bubbles inside the display in this between like these two. And there are positively charged particles, negatively charged particles. Positively charged white pigment. Apply a certain charging from the bottom. And that's how you get the black and the white. So you see these little cells in the microscope of all the ink bubbles. Each cell is not necessarily a pixel. A pixel is actually one electrode that's underneath this cellular network of bubbles. And so how it works every pixel is a TFT bed. So you apply a equals 1 with to and that creates a charge that would bring the bubbles up or down. I don't have. And so with a lot of these displays, they have they put checkmark glass movie. So the driver, the booster circuit, all that is already built in here. And all you need to do is polychrome MOSFET. So the ribbon connector here you see has this environment. Standard sparkless, talking with and also for the bubble something down. So all the circuitry is built into Budgie. With the displays, essentially you have two main kind of refresh modes. I'll show you the video that looks like. Here, this is good display. You can see more refresh, black and white, negative, and neutral color. This takes a bit longer, like 3 seconds. So, partial refresh is and in this little here, there's a comparison of the pros and cons of the different tools. When you do the full refresh, we get a cleaner image. There are no all the way down. With partial refresh, just bring this up. So there's a trade-off when you're designing graphics interfaces. The best way to go about it is to possible, and every now and then before refresh just to get the fault and state so you get the clean state. One of the trickiest things with getting these displays to update quickly and accurately, no wet time the voltage to run properly guys and bubbles. And that secret is if we get the quick control from my be in the firmware that's driving externally, they're meant to be controlled by the chip itself. What the local tables for this, since you're trying to drive, that's drive up and down. I mean, how long do you keep tuning for the device? That's a function of the temperature that's external to it. So because these when we tune a panel, the temperature has influence on how fast these levels move. And also, when you're transitioning from blue to white, white to black, black to white, there's a different sequence that you learn through experimentation on how do you get the fastest refresh. I'll start fast. All right, sounds good. Fastest refresh rate. So, see, all down. It's back up to 50 volts again, and everything's fine. So this waveform here is the timing of everything. So when the driver is trying to refresh an image, all the timings that you can do that. And so here's like a graph. Right. And the big one is to prevent DC load from if you have a you on your panel, all those including close to the top, you have to have. And so Machi, which is the dedicated that we're using today to play around with the use like. At a very high level, it's driven by MISP 32 P4. We chose this chipper because the oscillator as built in. So, right, we have 3 seconds, 3 axes monitor for protection, not clock. There's 4 buttons on each side to fusion, and the beautiful display. And built-in micro USB connector as well as a USB. So if you guys have your laptop set up, you just plug in the cable and program it that way. You can use it. Sorry. So the watch face we'll be doing for today's workshop. I'm a fan of the model. And so I found all these different watch faces for other watches, like Apple Watch, I think so obviously with Watchy you don't have black and white. So luckily for these design it's so I have some elements from these displays to fit into standard by 200 display. I like them anyway. I like to appreciate the time of the day, weather, diagram. I got all these elements to create a custom watch face, right? Which you see here, right? This is the design I came up with. But then to create that, like, what is the process? So with a lot of the smartwatches that run like Android or iOS, you have a full running Linux operating system on it, and you have a lot of graphic pattern routines and features that you can play around with fonts and characters. Like we know, running firmware. So you don't have a lot of those nice things to let you play around with the graphics. So essentially, all that text is one specific in font size. Are you watching the device?
Oh, sweet.
Okay, so I'm going to go through the code real quick from earlier. So when I mentioned the fonts that we're using for this watch face that you see on this, whoop, no signal? Weird. Basically, you would drop the TTF font into this tool here, and it would give you a byte array of all the glyphs in your fonts. And so what you would end up with is, this byte array of all the glyphs in your fonts, right? And here you see it's telling you which index, right, that the fonts map to. And so in your watch face class, you would basically just include it, right? So for the watch face, you would have 4 different font sizes. And so we would just include all of those in the header file. You also want to include the image.h and icons.h, and those are the converted images in byte arrays. And so, for example, we have the Vault Boy, right? It's a 57 by 100 pixel byte array image, right? So this is just black and white dots, right, for the image. Different pictures of the Vault Boy. And then for the weather, we have different icons for like Celsius, sunny, cloudy. And so when you do the print bitmap function call, it would print the image by loading this into memory. And so to build out the watch face, essentially you would inherit from the watchy class. You can see here. And the watchy class basically is from the watchy library. It has all the nice functions like reading the RTC time, reading the weather, setting up Wi-Fi. And then you would just override these calls: draw watch face, draw time, draw date, draw steps, right? And then here is the main function that gets called. So you override the draw watch face class function. And then you would tell it what to draw, and that basically defines your watch face. So we start off by filling the screen with black, right? And we put in like a dark mode variable, basically flips the screen inverted to black on white or white on black. You would set the default font size, set the cursor. And so if you look at the watch face image here, right? You see there's this like little bar and some text on top. So this is basically what it is. It's stat inventory data map. And then it would draw this bitmap, which is this thin white line that looks like a menu item thing, right? So these are the static elements on the watch face, right? Draw the bottom text, pip-port 3000, Robco Industries. That's what you see here. And then for all these other elements, they're separated into separate method calls. So draw time, draw date, draw steps, which is the step count you get from the accelerometer, draw weather, which is what you see here, and draw battery, which is the battery level. So each of these calls basically calls the graphics library and draws those onto the screen. We'll look at it closely. So for example, for draw time, we are drawing this giant block on the right here. So we are calling font size 28. We're setting the cursor, and we have this call like hour, 12, or 24. So basically it's 24-hour time or AM, PM time. And then you print out the giant letters, and then you change the font size back to 8 point to display the AM, PM that's at the bottom here. One of the interesting things we're trying to do here is the Pip-Boy, Vault Boy image here changes every 15 minutes. So basically what we're saying is, current times.minute, mod 15, then you would choose a random number, and then it would basically draw a different Vault Boy. The one that points at you, the one that smiles at you, or just the default one. What we could have done here is the white border that goes around the text. It could be a static image, but we decided just to, as a short proof of concept, to draw this with the draw line function call, right? And so all these numbers here, right? This is the X origin, Y origin, and then the X and Y destination, right? So these are kind of like pixel pushing. You figure out that by experimenting with the width and the length of that. Yep. Yeah. 0, 0 is top left corner. Top left corner. And then it grows, it extends by going down this way. So yeah, right and down. Yeah. Yes, yes. The set cursor coordinate is actually the lower left corner of where the text is, right? So if you imagine have the letter A, that this is the point where the cursor is. Okay? And that's specific to this Adafruit GFX library, right? That could be different for other libraries. Very similarly for draw date, you will see functions like current time dot something. Current time is a static variable that you pull in from the WashU library. So basically it reads from the RTC clock what the date and time is. So you just have to call this global current time dot month, and then it will give you the string. And so month short string basically just turns it back into like the 3-letter abbreviation. Let's see, the step counter, you could set define a variable for total steps for the day. So for this one, I set it to like 5,000. And basically when you hit 5,000, it draws a full bar into this image here, right? This is like a status bar. And it's just some math here, basically divide the step count by the steps goal times it by 100, and you figure out the number of pixels to draw on the bar to fill it up. And you use the fill rectangle routine to draw the progress bar. And the actual step count number down here. Draw battery, you're calling the WashU library again to get the voltage of the library. And then so for LiPo batteries, anything above 4.1, we'll consider it a full. Full is usually 4.2. And this is a rough estimate, right? Because the ADC on the ESP32 is not that accurate. So we're just using very high-level estimates of like where the battery is. And then we fill in the segments using fill rectangle and drawing it into the battery icon that you see here. Same with the draw weather. Behind the scenes, the WashU library calls the weather API, assuming that you have set up Wi-Fi already. And it will give you the temperature in Celsius or Fahrenheit, and also the weather condition as a code. And so each of these translate to a specific weather condition, like cloudy, sunny, snow. And so each of these we map to a icon that you could use, and that will display neatly right here. So to summarize, that's all the function calls to create this watch face. And then so once you override draw watch face and make all these function calls, you will have something like this. So you can get the entire code here. Basically try to compile this using the Arduino IDE, and you can play around with like where the location of different icons are and add your own twist to it. So I'll turn the lights back on so you guys can keep tinkering. Yes. Here you go. No problem. I do not.
you.